Perfect, almost all of you. So you should be very familiar with mappings. And mapping is essentially you map between, like this in the left is how all ERC20 contracts work, right? You have a mapping between an address and a balance. In the FHERC20 use case, the balance is encrypted. Technically, we can also decrypt the address. The problem is that if Alice transfers to Bob some encrypted tokens, their balance changes. And so while we don't see what actually changed in the underlying ciphertext because it's encrypted, obviously, we can still see that 2 records in the mapping changed. And even if the key in the mapping is encrypted, I can over time analyze this and understand and like build, pattern graphs, and like I can essentially over time leak the entire thing and understand who's communicating with whom. So this is not perfect. We need to protect access pattern to this storage system as well for anonymity. So what we've started experimenting with is a bucketing system. Now, a bucketing system is a sort of, I imagine, well, maybe you've heard about ORAM. ORAM stands for Oblivious RAM, Random Access Memory. Essentially, it means that you obfuscate your access pattern to the collections of data. So to an outside looker, it won't be, an outside looker won't be able to tell what record you are reading and what record you are writing. Okay, this is ORAM. This is the perfect solution to kind of obfuscate storage access. The problem with ORAM, and there are a lot of implementations and a lot of research on that topic, but ORAM usually is too heavy in the context of blockchains, right? It's too hard to implement efficiently. And so you have to introduce some relaxations. And for the context specifically of token transfers, we believe that a bucketing system goes a really long way to provide essentially almost all of the properties that you need. So what we do is that we take this storage mapping that we showed before, and we access and we use this as an entire bucket, meaning that if we split our mapping into multiple buckets, every bucket has to change to get like in a bulk, right? We can't only change one record in the bucket because this is what we had before. If we want to change anything in the bucket, we actually have to change the entire bucket. So how does it actually work? And for simplification, let's think of as only one single bucket. So what we do, and what actually FHE lets us do fairly easily, is that we have a collection of encrypted addresses and encrypted amount. If we want to change an address in this bucket, we actually want to change two records in this bucket. We want to, for example, if Alice sends to Bob, we want to decrease Alice's balance and want to decrease Bob's address, but we also want to change all the other balances. So what we actually do in practice is that we add 0 to all the other balances. And by this method, we actually like reshuffle all of the ciphertexts. So essentially, to an outside looker, we iterate over the entire thing. We change all the balances. And to an outside looker, it's indistinguishable which balances were actually updated. Okay? So in the case that we have only a single bucket in the entire system, this essentially gives you perfect anonymity because you cannot distinguish between any of the participants of the protocol, right? But this is very poorly, scales very poorly, right? Because the more participants that we'll have, the more iterations over this storage primitive we'll need, and the gas will increase, and so on. So this is a problem. So what we'll actually do instead is that we'll have multiple buckets. The buckets will be of constant size. It will be configurable. It's actually a trade-off between performance and the quality or privacy guarantees of the anonymity and the protocol. And so if Alice and Bob are actually in two different buckets, the only thing that will be visible to the outside is that two buckets in the system were touched. We don't know if they're changed. We don't know if the transaction succeeded or not. We only know that two addresses in two different buckets were communicating with each other, but we don't actually know what happened, or we don't know which exact addresses were touched internally in the bucket. How it actually looks like in the code. So if you are familiar with multiplexers, this should be fairly understandable to you. So we have the select method, which essentially, well, we can skip straight to the simpler version where you check if there, like you iterate over the entire bucket. You have, as you see, receiver at the top of the function. The receiver is actually encrypted address. All of the addresses in the bucket are encrypted as well, and then you go address by address and you compare between them. And the comparison actually gives you a Boolean, a 0 or a 1. And you take this Boolean and you multiply it by the value, so that for every record you either add 0, because you multiply it by 0 because they're not comparable, or you actually adding the value. In this case, you need to also do the other side of the subtraction as well, obviously. But this is essentially how it works, fairly simple. This is here to demonstrate that actually writing with FHE in Solidity is essentially quite simple. You don't need to like build special circuits or anything like that. So it's still Solidity, it's still composable with other protocols, so that's pretty cool. Yeah, so what did we ended up with? We essentially ended up with a system that looks very much like ERC20s as we know them, but they're encrypted. We also received some degree of anonymity. And so again, this is like configurable. The larger the buckets, the performance, we will hurt performance a little bit, but then the anonymity set will grow or like for every participant. The only thing that is known to the outside is that two buckets have communicated or touched in the protocol, but we don't know which record inside the bucket. This, again, very similar to the other protocols with the railguns and so on, that mainly helps the receiver privacy, and we still have this problem of who pays for the gas for the transaction, right? So here we can just adapt to other solutions of like using private relay networks and so on. So this is essentially like a problem that we can just it's essentially solved in a way. Definitely can be improved, but we have a solution for this problem. Now to the elephant of the room, and again, as was said before me, FHE is slow and so on. So it's actually more of a stigma these days. And this you can see what we actually managed to achieve with this POC. So we ran the POC on CPUs and GPUs. We essentially got a performance of 1 TPS with a bucket size of 100. So that's not perfect, but that's not too bad. I would argue that I'm way more comfortable, or I would argue that some people would much rather using actual MetaMask and like the existing tools for their transaction, while being indistinguishable with 100 other or 99 other users of the protocol, which is not bad at all. But as you see, the problem is that as you stack hardware on top of each other, we actually get diminishing returns. So it's not improving the performance linearly, and we kind of get this logarithmic graph of the size of the bucket that I can actually achieve. And this, by the way, the size of the bucket and the TPS is interchangeable. So if I have a size of 100 with 1 TPS, I can actually achieve 10 TPS with a size of 10, with a bucket size of 10. So again, this does not scale very well. And the question is, can we scale this better? And what I'm about to show you in the next slide is actually we showcase this for the first time. So we are fairly excited about this. or rather very excited about this. We are building in Phoenix a new novel FHE scheme, where our goal is to reach Visa level performance and throughput, right? We saw the graphs. I don't know if you guys saw like comparisons between like Visa and X402. Like we're seeing like the blockchain throughput kind of increases over Visa already, but Visa essentially gets 10,000 transactions a second, more or less, and we want to reach the same. This is very rough numbers, very like, you know, POC level, but essentially we get somewhere in the realm of 1,000x throughput from the current state of the art. The scheme is very good at arithmetics and very highly parallelizable. So it's a very good match for a use case like transactions. And yeah, this is something that we're very excited about, and you know, more details will come next year. We hope to release a paper soon, and obviously integrate it into our core processor. This is essentially it. We have a few links here. If you're builders and you're interested, you can keep in touch in our blog and documentation. You can follow us on Twitter. And if you guys have any question, I'm out of time, but you can catch me afterwards, and I'll be happy to talk. Thank you very much.
Hello. Slide is a Ethereum. Okay. Nice to meet you guys. My name is Eugene. I have been in crypto since, can you hear me, right? Since 2018, and I started by running a fund at the time as a CTO and co-founder of the crypto fund, and we invested many great projects like you guys. And then we recently won a Sony's incubation program last year, and now we are moving into this FHE Ethereum using our Web2 proven tech stack. So what Ethereum is? So Ethereum is a like kind of Web3 initiative from the Crypto Lab, which has been in FHE for Web2 for the last 7 years. And we are bringing this tech stack named CKKS into Ethereum. So we are not like, so I think this like general FHE coprocessor for Ethereum and blockchain, I think the Jama and Phoenix are already doing very well. So we are not getting into that path. We are more like, we are trying to find what would be the best fit for our FHE stack. So some directions like we are exploring right now is like, one is universal digital passport for running on Ethereum. Another is a federated AML risk scoring, and also private payment for institutional finance. So these are more like, when you see the first two examples, like a digital passport and AML risk scoring, these are more like AI and vector operations, and we can bring that to on-chain. So privacy is a core to Ethereum, and we have more to improve, so we are working on that all together here. So on-chain, we have developed the GK for last 7-8 years, and now we have some more like we have some like trust assumption of chain data and computation. So we still trust some centralized data silo, and we also have some trust on the regulator and audit, not purely on math. So so actually I prepared these slides for more like a novice people, but I don't need to explain to you guys, I think. But major difference between GK and FHE is, so GK proves the is like verifiability, but when you first generate this proof, you have to trust the computer that generate the proof. So we can protect the data side. So yeah, so I'm gonna skip that. So a little more about our tech stack, CKKS. So we have been working on Web 2 side, and we started with the approximate floating number FHE. Then last couple of years, we made a very great improvement on the discrete numbers FHE too. So we are very strong at the privacy preserving AI stack, and also we are very great at scaling arithmetics. So for example, when you train AI model and then when you run inference on AI model, we can run it with the encrypted features. And this vectorized and then SIMD, the single instruction multiple data friendly APIs are already used in production. So we have a working demo that we have tuned Llama AI model, and we trained it privately, and we inferenced it, and we also did some private RAG demo on encrypted data. So it's a little, so the Taurus FHE that like Jama and Phoenix are working on that scheme is very different from our tech scheme that CKKs are doing right now. So it has its own pros and cons, and we are more strong at vector operation. So who are using our tech stack right now? So we have been deployed and validated by South Korean military secure analytics, and also some enterprises like Samsung and IBM and TOS. TOS is like a Venmo in South Korea, so we are using it. We have been used by them. So how it's working is so when you see the data, previously, like even though you encrypt the vector data, when you query it, you have to decrypt the vector and then do the searching. But from the CKKS, the query is encrypted as well, so the result is also encrypted. So it's fully encrypted, fully private. I'm gonna skip this. We all understand this. So the point of this slide is we can use both GK and FHE so that we can complement each other, as the Phoenix already mentioned. So one example that we are thinking right now is the KYC reality. So currently, when we do the KYC, we have to trust, or like we have to collect the full KYC data first and then retain it for years, because government agencies and enforcing agencies, they require to keep the original data for the auditability. When accident happens, they will come and look at the original data. GK is very great technology to prove that this person already passed the KYC, but in case of the accident, you still need the original data. Then that's where Ethereum comes in. So all data is encrypted in the database. So only when it's required, the data is decrypted, or data can be evaluated in our FHE circuit, so that this person's original data is there, and then we have done correctly the KYC. So how it works is the person first send the KYC data. So the KYC issuer can do some, like they do the verification of the KYC data, and then they verify and sign and store the data to our database. Then we hold or encrypted some identity information and also net worth, income, address, and plus some signature. So we store the encrypted data as an escrow, and then we send encrypted credential to the holder. So the user's wallet hold encrypted credential. Then, when the user uses that KYC proof to some DeFi protocol or other use cases, then the protocol want to verify the KYC for, let's say, institutional finance or other cases. Then it first requests, hey, you should prove your net worth is more than 1 million. Then the user fetches data from our data escrow, and then fetch the encrypted data, and then decrypt from their wallet, so from the client side. So still, we don't know any raw data from our side. Only user can decrypt it and then generate the GK proof from user device, or they can also use a TEE. So so they can use other tech stack for keeping their privacy. Then the public input is threshold that the protocol required, and the private input is actual net worth, and the proof is their net worth is more than threshold. Then send that proof to protocol, then the protocol verify the proof on chain. Then they grant the access to their protocol. So once they proved their KYC on Ethereum first, then it can be used for multiple protocols. So just verify once on Ethereum and multiple use cases. So we are exploring this idea about privacy preserving passport anchored on Ethereum, and underlying identity and KYC attributes are stored as a FHE encrypted vector. So you prove once and reuse safely, and devs see the risk scores and attributes, never PII. So it can be compliant and or private and auditable. So in this case, the Ethereum as a confidential we work as a confidential data and computation layer. So we can generate multi-keys, like for example, one is user key that's always needed, and some regulator key, and arbitrator key in case of some claims and dispute. And we store the encrypted data and access policy. And the regulator only in the emergency access, like when they deem that there is an accident, then they require to decrypt the original data. But users should agree with it, or we have a more design on this time lag and other more details, but I will skip it this time. Another case we are also seeking is a federated AML on encrypted feature. So more institutions, the traditional institution coming into the Web3, and that they hold a lot of Bitcoin and Ethereum and other digital assets, they want to be safer when they store their data. But we all see a lot of accidents happening every year, right? So a lot of hackings, and but the problem is each institutions, they have their own data. They cannot share the data each other because of this regulation. So Coinbase only sees their own transaction. If it's suspicious, then they report to the FinCEN. So these kind of schemes are implemented for every country. And criminal moves to the Binance, then they cannot see it, right? Then from the Binance, they cannot see the Coinbase data or other exchange data. So there's no context from other than the Binance database. So they say, oh, it should be okay, but they approve, then boom, there's an accident. So that's how current AML and then hacking or attacks are working. So what if these institutions can cooperate and work together? So they share the data together, but not the raw data, but encrypted data. So they cannot see the raw data, but share the data in encrypted way, and then they can run the shared machine learning model to better detect the fraudulent actions. Then this Ethereum AML scoring model can return the risk score to all participating entities, then they can better detect the fraudulent actions. So this encrypted ML model, it can be logistic regressions or other model. So we are very strong at this kind of vectorized operation, very fast and scalable. And it can run on both CPU and GPU. When you add more GPU, it's more scalable. So when a high risk is detected, then it's notifying to every institution. So maybe this institution can like freeze that fund, or they can work on their own prevention actions. So the problem was every custodians, exchanges, and institutions, they run their AML model in isolation with only partial data, but we enable collaboration without revealing PIA or raw data. So they can run the shared AML model. And yeah, we are very strong at this case. Why it was not available before? Why it's available right now? Because this FHE bootstrapping was very heavy and it's very costly action in FHE operations. And Ethereum made a very great improvement in these actions bootstrapping, and also we made a very good improvement on the SIMD, slot packing, and also GPU acceleration. So now our performance is now practical. So until last year, it was like a very limited practical level, but this year also we made another great improvement, and now we believe we are prepared to be in the market. So the benchmarks, so the configurations are like something like this. So it's some specific demo benchmarks that we have done before. So when you run this bootstrapping on one CPU, one thread, it took like 6.7 seconds. With a 16 thread, 1.1 second. But one GPU with the RTX 5090, which cost only $2,000, it's not like H100. H100 is like $20,000 or $30,000 in this market, but this one is a very cheap one. So, but in this cheap GPU, we achieved 14 milliseconds for one bootstrapping. And one example is, what the TOS, which is financial institutions in South Korea. They use this Face ID payment, so it should be very secure. It's already running. And this case, biometric searches, one-to-one authentication. Against the 65K database search, it took 25 milliseconds with using one GPU, the RTX 5090. And against the 2.6 million database, it took 1 second. So it can be scalable with a multiple GPU. And so think about if we add 10 GPU or 100 GPU as like succinct to our other ZK provers, they are running huge size of the GPU machines. So if we scale like that, then it can be way faster. So this is another performance benchmark. So we had this benchmark in our paper against the OpenFHE. So basically, we compared the addition and multiplication and bootstrap. So it has a different numbers when we use a CPU and GPU, but the best benchmark is at the right side. So now it's like multiplication and addition are in microsecond level. We don't say we are perfect at this moment. We are still improving the constraints so when we like expanding into the Web3 and Ethereum domain, then there are still things that we have to consider. Like first is more performance and better performance. The second is key management and trust. So Jama and Phoenix already covered that, so I'm gonna skip it. But the decryption key management is very important, and also developer UX. So we are thinking about what would be the best developer UX, developer experience for using the CKKS. So we are like, eventually we can be generic in the future, but when we first start, we want to be focusing on very specific use cases where our CKKS stack can be really strong and perfect at. So I believe some AI, decentralized AI initiatives can be our good example. So we want to co-work and collaborate with the Ethereum community, so especially people here. So our tech has our own pros and cons, and we are just starting in this space. So we have a better tested FHS tech in Web 2, but creating, making the Ethereum and Web3 product is a little different story. So we are still exploring, and we are looking for some teams to co-work on this together. So Ethereum, of course, and some infra teams or layer 2, and also privacy-focused project with a application layer or infra layer. We are welcome to co-work. So please join us. It's a Google form, so you can join and you can hear faster than others about how we improve and what would be the latest status of CKKS and Ethereum. Thank you.
Hello, everyone. Yeah, my name is Gurgen, and today I will talk about how we at our team trying to build FHE more practical for developers and bring it to production. As all of us knows that privacy is one of the important issues that we have in blockchain. We solved almost all significant part during the last decades, and privacy looks like the main issue for the blockchain. And FHE as fully American encryption looks like the great technology with great potential that can solve this problem. And since the beginning, different schemes were developed. This is only just the main directions, 3 families of the scheme, and which is important to understand that there is no universal scheme for everything. And when you want to have scalability, you can use something like CKKS, BGV. If you need to have token transfers, TFHE family, FU family may be better, but all of these families and all of the schemes has limitations and advantages. The same about libraries. We have different FHE libraries with different licenses, with different models, different languages, etc. And the challenges that we have today, I grouped it in 3 main parts. The first one is efficiency, and to be honest, I believe that issue with performance will be solved in a couple of years, and at least right now we already have great progress. FHE is more than enough for a lot of applications, but if we talk about some general computations, FHE more slow than operations over plain text. The second one, for me, looks like the most difficult part, because approach using global FHE keys that we see when we try to build some encrypted private shared state based on very weak security assumption and decrease security, quantum security of FHE to the security of the threshold protocol. At the same time, if you don't need to have private shared state, and if you don't need joint computations, you can eliminate this factor. Another thing that was also mentioned in the previous talk, the lack of developers ecosystem, the lack of what we call application layer. This is user experience for developers. And I will focus today on the third part and explain how we are solving it. This is the general FHE stack for developers, and not only for developers, how it looks like. Developers working on the first 2 layers. Usually developers may work with transpiler or compilers or directly with libraries. And the problem that current compilers, we can't say that compilers can help a lot for developers, because the main issue for developers is the limited basis of operation that you have from FHE scheme side. And compilers will not solve this issue for you. And to understand better the problem, I like to consider the case based on neural network. Let's consider that we have some general neural network, and we want to have privacy-preserving inference. And all computations, significant part of the computations usually happens in neurons, the same for all neurons. And we have plain text input in the open way, and we want to have opportunity to put encrypted input. In this case, we just need to change the computation inside neuron, which usually looks like this: 2 parts, weighted sum at the first step, and some evaluation function, activation function as the second step. And if we change the input to encrypted data, we will face, as a developer, we will face the issue with the second part, because it will not clear how to evaluate functions like ReLU when you have very limited bases, when you can do only addition and multiplication. And compilers will not help to you, because compilers will probably simplify the writing the code and communication with the library, but will not provide you opportunity to evaluate this kind of function. And developers will work, as I said, on the cryptography libraries layer or transpiler, compilers layer. And the way how you can try to solve it usually can be grouped in 3 ways. You can try to build some polynomial approximations. You can try to play with different packing technique and add more informations. Or you can play what's called functional bootstrapping, sometimes also called programmable bootstrapping. But initially, what's really needed for developers, it's some kind of black box that will evaluate what we need. In this case, just black box where we can provide encrypted input and get result of the evaluation of the function, ReLU namely in this case. And we need a lot of these kind of components. We call it FHE components, and we need a lot of these components to be able to provide good experience to build applications. If we have these components, we can just consider all of FHE applications like some kind of circuit which consists of different components. And these components may be with different schemes. You can just run computation over some parts of your logic with one FHE scheme, then make scheme switching, use different schemes. And the scheme I mentioned, like bridge, that can be used to make different scheme switching, etc. And this is the layer that missed, in my opinion. So it's the layer between cryptography libraries and developers tooling like compilers, is the layers of FHE components. And the first thing we do, we build this layer. And we do it through our platform, which is called Firma. It's benchmarking and challenges platform, where everyone can try to contribute with components. We recently published the first part of components. It's the joint work of strong community, state-of-the-art components with great performance. It's published, you can find it. Source code also available. Another interesting thing about execution part. Okay, we built execution, we built developers tool, but how to launch evaluation? And again, the problem that even if you can use GPU, even if you can use ASIC, you don't have some universal execution layer. And for some components, for some execution logic, GPU may be the good choice. For another one, CPU may be more than enough. And in our vision, the best choice to provide execution layer is some kind of heterogeneous network of different actors with different capabilities to evaluate different functions. Some actors may be focused on evaluations on specific components. At the same time, you maybe choose another actor which will provide better performance for another components. And in our vision, it should be looks like this. You have the application which consists of different components, and you have the network of heterogeneous actors with some kind of verification on top of it that can evaluate components and your application. We published this work, call it Decentralized FHE Computer. It's published, open sourced. And general computation looks like this. You have application that on orchestration layer presented as the graph, and you have different 2 layers of actors, main actors and fallback actors, which communicate with each others that launch and evaluate your logic. And in general, the stack for developers and for FHE ecosystem in our vision looks like this. At least we are building this kind of stack. On the first level, you have developers tools like compiler, you have components layer, cryptography layer and mask layer, and execution layer. And our team is working on 3 of them. We are working on execution layer, at least we provide orchestration for it, and we built 2 of the first layers. On top of it, we build different applications. I didn't put in the slide, but the recent work regarding PIR that we have allows us currently to make PIR requests to Ethereum network without communication, so it's not interactive protocol, but we can do it with some kind of sharding and do request for encrypted address and get result about encrypted addresses in this model with less than 5 seconds. So in the database, you have hundreds of million addresses, and you can just get information in just some kind of 5 seconds. We will publish it a little bit later with more details. And that's it. Thank you for your attention, and any question if you have. Thank you. Yeah. I was super fast.
A question. So you showed the FHE computer with the different computations for different parts of you know. So my question would be, do you see different components running also different schemes? And if so, like specialized schemes for each component? And if so, how easy it is to actually scheme switch between them? And how latency does that?
Yeah, good question. Thank you. Scheme switching generally is some kind of bottleneck. It's not too easy right now. But in the compiler infrastructure that we built based on, if you know, MLAR stack, you have some intermediate layer that allows you to make this scheme switching more easily, but it's still hard part. It's just, but it's not needed for most of use cases. It's just the vision for the next future when you will have new schemes, etc. Yeah, thank you.
Okay. Can you hear me? Yeah. Okay, so my name is Miha, and I will talk about what could be some lessons from ZKPs for FHE. So to help speed up the adoption of FHE. Because the thing is, the evolution of ZKPs was really fast. So the progress in the research of zero-knowledge proofs has been remarkable, but perhaps even more impressive is the adoption of this research in Web3. And I think there might be no other industry actually where the research comes so quickly into the industry as it is with ZKPs in Web3. Just for example, these two papers, Grove 16 and Plonk, which you all know, these two papers are kind of household names in Web3, which is really surprising and fascinating to me because it's very high-end research, which is now part of the community. What about ZKPs before Web3? even before I joined, before I started working in Web3, I was interested by the concept of anonymous credentials, and there was, for example, this paper by Jan Kamenisch and Anna Lisanskaya about anonymous credentials, a really nice paper, and already in 2001, so it's 25 years old. And it was not only a paper with a nice idea, it was also that IBM actually wanted to make a product out of it. So they built Identity Mixer, which is a cryptographic protocol suite for privacy-preserving authentication, which should be very much familiar to all of us. But there was no adoption, basically. So I was thinking a bit, what might be the reasons that the adoption of ZKPs in the last years was so rapid in Web3. And I think the main three reasons are actually the shift to general purpose proofs. Then we, of course, have now blockchain as a deployment layer. And also, which is, I guess, very important, is the culture of Web3 and its openness. So the first one, the shift to general purpose proofs. So like the one that I mentioned by Kamenisch and Lisanskaya was a very specific proof about anonymous credentials, while later Grove-Sistine and Plong basically transformed zero-knowledge proofs from a toolkit for identity to general purpose proofs. And this unlocked many possibilities like roll-ups, ZKVMs, and all kind of other things. Yeah, so what about general purpose FHE? Is this a problem for FHE? I would say no, because we already have different schemes there. So we have integer FHE. For integer arithmetic, we have approximate FHE schemes, which are very suitable for machine learning and AI. And we also have scheme switching. So we can, for example, the number comparison might be difficult to achieve for CKKS, but you can switch to TFHE, for example, and do the comparison there, and then switch back to CKKS. So I think that's not a problem for FHE. Then the second reason for this fast adoption, blockchain as a deployment layer, of course, that's kind of the same, because yeah, with blockchain, suddenly there was a real testbed where new cryptographic ideas could be deployed almost immediately, but this is pretty much the same for FHE as well, right? And this created an ecosystem where fast prototypes and shared libraries could emerge almost overnight. And also, one important thing was that snarks turned out to be a perfect match for blockchain because they are short and can be checked quickly on chain. So for FHE, yeah, it's similar. We have a deployment testbed and a live adversarial environment that forces real engineering. And also, I think new research is actually happening in public now, also in FHE context. However, it's true that the situation is a bit different, considering that FHE is not a perfect match for blockchain because of the large ciphertexts, which mean large gas costs and latency because of bootstrapping. But people found workarounds for this, like coprocessors, as we heard. So that's kind of solved as well. But what about the culture of Web3? So when I started working at EF, like in 21, we were working on ZKVM, and what was really surprising to me was that we openly collaborated with other companies like Scroll and Loopring. Of course, the common goal was clear. We all wanted to build a robust layer 2 solution for Ethereum. But still, for most industries, I think you would expect competition and secrecy, not engineers from different organizations actually openly exchanging ideas and debugging each other's code. And also, from the very beginning, there were open source libraries in Web3 like LeapSnark, Bellman, ArcWorks, Halo 2, and there was a great community behind these libraries, and most of these libraries were actually permissively licensed. There were some projects which were closed source, or perhaps they were not permissively licensed, but I think they are mostly gone. So that's something I would say. Then also there are various platforms which helped with the adoption a lot. For example, the Zero Knowledge podcast, then the ZK hack. Also, for example, a nice thing from 0xSpark is ZK Backtracker, where the common vulnerabilities found in the libraries are published, so the developers can be attentive to these kind of things. And also, I think people realized from the very beginning that they need to provide DSLs and compilers and in intermediate representation languages, because like from the beginning we were writing R1 CS constraints directly and custom constraint gadgets, but this is kind of difficult for people that are not cryptographers. So in ZKPs, a lot of these new intermediate languages were built, and the moment this happened, actually other normal kind of developers started to write ZK programs, and proof of concepts were built fast, and new teams were entering the field. So what about these intermediate languages for FHE? I think that's even more important for FHE than for ZKP, and that's actually also what Gurgan was talking about, because FHE is in a way even more complex than ZKP, because you need to consider parameters like noise growth, modulus switching, scheme-specific optimizations, and much more actually. So if you just have a look at a simple number comparison, so if you have encrypted two numbers and you would like to homomorphically compare whether they are the same, this should be kind of simple, right? It's very simple operation. So you have encryption of x1, encryption of x2, and just homomorphically compute whether whether x1 is the same as x2. But it turns out this is very difficult actually, and there are many parameters to be configured to enable you to compute this. So in general, the idea is you subtract one number from the other, compute x1 minus x2, and then you can use bootstrapping, functional bootstrapping, for example, TFHE bootstrapping, to compute it. Because bootstrapping is not only for reducing the error, is also for the evaluation of a function, and this comes pretty much for free, right? But there is a catch. This actually works only for very small numbers. For like, you can directly use TFHE bootstrapping only for numbers that are smaller than 16. And of course, there are many use cases which require bigger numbers. So, of course, and so if when x1 minus x2 is not small, then you need to actually do the composition into some base B. Then you need to iteratively use homomorphic floor function, and then for each function you actually call 2 or 3 bootstrapping operations. So and obviously the performance goes up a lot. So this is the log p is the size of the plain text. So the size of the numbers that is supported, how big x1 minus x2 can be. So if you increase it, then the performance obviously goes down because of the number of bootstrappings. But there are many other parameters involved which needs to be configured, like the ciphertext space, the base that you are using for the compositions, and all kind of these kind of things. And also, for example, that's not the only thing that you need to configure. You only need to configure beta, which is bootstrapping noise, and beta 1, which is the error of the input ciphertext. And so, based on this, you compute actually the ciphertext space. So Q, you compute it using by this formula. So logarithm of Q is logarithm of P plus logarithm beta plus beta 1 plus 1. And the bigger the Q is, the more bootstrappings are needed because the complexity scales linearly with Q. What's more, you need to configure the probability of an error. So for example, these schemes usually are configured to have the probability of an error smaller than 2 to the minus 32. But for blockchain, this is not enough because of the number of operations. You need to have this probability much lower. So you need to configure actually beta differently, because beta is, so error is, which brings noise to the ciphertext, is sampled from Gaussian distribution, which is kind of this kind of graph. And the bigger the beta is here, the less probable is that you will sample the error. When you need, if you have a use case where you need the smaller probability of an error, then you need to configure, for example, different beta, which needs to be large, and that means the ciphertext space will be large, and also the computations will be slower. Then also you need to configure the security level, for example, because the ciphertext is computed. Ciphertext C is computed as message M scaled by some K plus the inner product of two vectors A and S plus some noise E, and the security level is basically depends on the dimension of these two vectors. So that's another thing to be considered. And also different methods, different schemes actually have their own merits, and the selection which one to choose is actually application dependent. And that was just for simple number comparison. So if you want to go to arbitrary evaluation, it's even more complex. So you have different schemes, and some are better when the precision reaches 10 bits, for example. Some do not support multiplications between ciphertexts. Some are better suited for a larger number of evaluations. So for somebody who's not cryptographer, who's not FHE expert, it's kind of impossible to set up all these kind of parameters. So I think if we need to convince users to start playing with FHE, to adopt FHE, I think we need to engage the community, and this can be done by the following things: by having approachable DSLs and intermediate representation languages that actually hide cryptographic details and let developers write normal code. I think there needs to be playful sandboxes and interactive demos, and there needs to be high-level compilers that translate, for example, Python and ML AI workflows into efficient FHE circuits. And we need to have benchmarking tools and visualizers so developers can see how parameters actually affect the noise and cost and all other things. So in this way, I think FHE can also become kind of a household name as ZKP is today. I think it's important to do this. So yeah, that's all from my side. No questions? Yeah.
What would be your message to companies maybe like, what would be your message to a company maybe like a Crypto Lab, for example, that we heard from, on how to engage with the Ethereum Foundation to accomplish some of the goals that you set forth in the last slide?
Yeah. I already told Eugene what I think, and this is actually open source your libraries under permissive licenses and engage the community. Because one other thing that was really strange, I mean, kind of surprising, before I was working in Web3, still on this kind of Kamenisch-Lisianskaya kind of proofs, I was talking with a researcher from Vienna, And I said to him that I think everything should be open source, but and he said, come on, if it will be open source, nobody will actually read it. Who reads the code? Nobody actually spends time on this, and this was like 10 years ago, and now we see in Web3 that's actually not the case. People audit the code, read the code, contribute to the project. So I think that's important.
Thank you.
Jay?
How much of a role do patents play in sort of inhibiting the growth of FHE in the ecosystem?
Sorry?
How much of a role do patents in FHE systems play in inhibiting the growth of adoption of FHE in the Web3 ecosystem?
So I didn't get it. Can you say it slower?
Patents.
Patents.
Yeah.
Patents.
Right.
So what about patents?
Like, I mean, how much of a role do they play in sort of inhibiting the adoption of these systems generally?
That's actually one of the problems. This scheme, Kamenisch-Schlesianskaya, was actually patented, and this, I guess, that's not the way to go, because you hinder the collaboration and the adoption of it. I'm not familiar with it. Okay, thank you.
I think you needed to select the screen you wanted to mirror. Yeah, there.
Oh, I see.
Entire screen or window wrap? Yeah. And there you go. It's the full screen, or do you need to press the green? Oh, there it is.
It is full screen. Wait, I'm not able to. Do you have?
We don't have a clicker because.
Oh, I see. Okay, fine. I'll do this. Hello. Today I'll be talking about Phantom, how it works. First, I'll introduce Phantom, what Phantom is, and then I'll be talking about how it works, performance, and so on and so forth. And I'm Janmajay. I work for a research organization called Phantom Zone, and the website is phantom.zone. Okay. Wait, there you go. What is Phantom? Well, the way I like to think about Phantom is that it's a FHE virtual machine built using FHE circuits, and it can execute encrypted programs on encrypted inputs. Okay, so you can take a program for someone else. So as a developer, I can write a program on my laptop. I can encrypt it. I'll tell you what encryption is. Like, just take the binary, encrypt it, and then you can give it to a beefy server. Now, this beefy server can execute the encrypted program on encrypted inputs coming from anyone. Okay, and I'll get into the details of what this means. And first, why develop Phantom in the first place? Well, Phantom is a virtual machine. Since it's a virtual machine, it can execute any arbitrary program. So you're not limited to a circuit model. It can have input-dependent execution. So you can, the way a normal virtual machine works. It can, there's no exponential increase with the branching. So normally in circuit model, if you have multiple if-else, like nested if-else, you'll have to pay for each and every branch that the nested if-else executes. In this case, you just put a program counter, and that's it. So you do not have to pay for exponential increase with every nested if-else. You also do not need to, fortunately, make your program constant in runtime, because it's no more a circuit model, it's a virtual machine, so it works like a virtual machine. The second thing is that it's easy to work with. So in Phantom, you simply write your program as a simple Rust program, as you usually would. You do not have to think about what is a circuit, what is FHE, and so on and so forth. You simply write a Rust program as it is in Rust, and that's it. Phantom would execute it. One consequence of building a VM, we didn't realize it when we were starting with this. One pretty good consequence of building a VM is that you can write programs, and since you encrypted the programs, you can have programs with hidden constants, hidden routines, and what else? And instructions as well. So even you can have a function in a program that itself is hidden from somewhere else. So probably what you can do is that you can have a program that would have a hidden secret, and the hidden secret would sign things for you if some particular condition is satisfied. Okay. So how to use Phantom? Well, to do that, before that, you just write your Rust program as it is, and that's it. Like, all you have to do to use Phantom is like just write your Rust program, and that is it. But in this case, I'm being a bit optimistic here, because you have to account for the performance bottleneck of FHE, and that would limit the type of programs that you can write. But if FHE was very fast, you can just write any program that you wish, and that's it. And to make this more concrete, I would show an example. Okay, so let's take an example. The goal for the example is that let's just write OTC code generation program. What does OTC mean? OTC is over-the-counter tests that would facilitate bigger trades for you. For example, if you're a big whale, you want to trade, I don't know, BTC to USD, you cannot go to a centralized exchange or even a Uniswap. What you have to do is like contact OTC desk, tell them that you want to trade from BTC to USD, and they would facilitate trade for you. The goal that we want to have, is that we want to facilitate OTC trades, or at least OTC code generation, so the desk can code to you what the trade would look like with encrypted intents. So my trade intent of going from BTC to USD is encrypted. Again, how does it look like? So the client sends an encrypted intent to the trade to trade BTC to USD pair, and the OTC desk executes their code generation algorithm on the encrypted intent and sends it back. Okay, and now I'll be showing you a simple example of how to code this out. I have already coded it out so that I don't waste my time over here and not run into bugs. But I'll show you what the program looks like. And to be more real, the program actually sort of like tries to simulate what an OTC desk would really do. So, for example, the coding algorithm would take multiple variables. For example, it can take the client profile for client-dependent rates. So if the client is a prime institution, then the OTC desk would want to offer better rates to them. The OTC code algorithm would also adjust for the size. So for example, if the size of the trade is very large, it can move the market, and hence you will have to account for the spread. The OTC desk would also want to provide volume discounts, just be nice with the customer if the volume is large, and if the customer is a prime customer. Cool, so how do we code this out? Which is why I have an example. Okay, so this is the structure of how a Phantom program is structured. Okay, so you have a host crate, and you have a guest crate. Guest crate is where you write your Phantom program. which is essentially encrypted afterwards. So I'll go to the guest crate, and I've already written the program for OTC code generation here. The main function to focus on is this particular function. As you can see, this particular function is simple Rust. Are you guys able to see this properly? Oh, you're able to see this properly, right? Do you want me to sort of increase the font size? Cool? Okay. So as you can see, you're simply writing Rust programs here, nothing else. And this particular main function essentially does what I described before. It takes in the it takes in the market order, which is the input. And this is, at the moment, it's not that developer friendly in the sense like there are things you need to do, but this is the way to read the input in the VM. It takes the market order, which includes the client information, the trade, and the market data. Market data is like what is the market what is the volatility of BTC USD pair, and so on and so forth. And then it first computes the base spread, and the base spread is another function. Okay, so I'll go to the function. The base spread simply checks whether the client is either institutional, retail, or prime, and then returns the base spread as per that. And then it computes and then it adjusts the base spread as per the size, which is why we call this particular function. And as you can see, this particular function sort of like takes the size of the trade, computes how big of a volume it is compared to the volume traded in this pair for the past 24 hours, and then as per that sort of returns a size factor. And size factor would change the base spread. You do not need to understand how why this is done, but I'm just trying to show you that if you were writing this OTC program yourself as an OTC desk, that's all you have to do. You just have to take your Python code and put it in Rust. And then there's another function called volume discount to give discount based on volumes, and this is this function. So if you're a prime or an institutional player or like a prime or institutional client, you would get a volume discount if your volume is large enough. And then you calculate the final spread, and then you convert that to USD, and then you give the ask price and the bid price. Again, the ask price and the bid price, which is the returned value, is encrypted, and it is sent back to the client. Make sense? Surprisingly, you would notice that all of this is done on F32. We're not using integer arithmetic here. We're using floating points here. And we did not develop special routines for floating points. It's just like the compiler works out of the box. We're just simply leveraging Rust to RISC-V compiler, and all we had to do was build a circuit for the virtual machine of RISC-V for a particular instruction set. Okay, and everything works out of the box. You do not have to care about the thing that Miha was mentioning before. You do not have to care about noise growth. You do not have to care about failure probability. All of that is taken care by fixing a particular circuit, which is the VM circuit, and everything works out of the box for the developer. Okay? Now, I've shown you one program, which is this OTC program, but I would like to stress the point that in this case, although in this particular use case, I suppose the OTC desk would be running this encrypted program, so nothing needs to be encrypted, everything can be public, only the trade intent needs to be encrypted. But it could be the case that someone else was running this program, and there was some proprietary information in this particular encrypted program, so there's no reason why this particular routine cannot be hidden from the third party, right? So what the OTC desk could do is that, in this program, this particular routine becomes encrypted, and it is sent to a beefy server which executes trade intents from clients. To make this a bit more concrete, I'll show you another example for which I'll have to spin it up. So in this particular example, there's a hidden string. I'll show you, just give me 1 minute. So this is another very simple example. And the goal of this particular example is that, just pay some money out to a person who guesses the right string. And the right string in this particular case is Mississippi. So it showcases the idea of hiding constants inside the program. So you can have a program with hidden constants, and if in this case, if you're able to guess the correct string, you can probably get some money. But there's no reason you cannot have a secret that signs or something else, or sign the Ethereum transaction for you if something matches, some predicate matches. Okay. Cool. So this sort of showcases how to use Phantom, and it sort of like nails the point that as a developer, all you have to do is write the program. Everything is taken care of at the back end. We do not have to care about the noise growth. We do not have to care about the circuit model and so on and so forth. Just write the code, and that is it. Okay, so architecture and performance. Coming to the architecture of Phantom. This is a particular schematic that John Phillip from a team sort of drew out to explain me how this works. It has, I would say, 4 main components, and this middle routine is sort of like connects all the bottom 3 components. What it essentially does first is that it will first read the instructions from the ROM. Okay, just to give you more clarity on what a VM is. VM has a place where it stores an instruction. It has a cycle, and the cycle has a RAM, and so on and so forth. And it has registers as well. Okay, so first you read the instructions, you execute the cycle, and the cycle has 3 side effects. It updates the RAM, or it updates the registers, or it updates the PC. Okay, so the first task to do is you read the instructions from the ROM. ROM is like read-only memory. And then in the Phantom VM, which is the FHE virtual machine, you have to prepare them, and I'll get into details of how to prepare them. But once that is done, you have to execute these 3 boxes in parallel. The first box here updates the RAM, the second box here updates the register, and the third box here updates the PC. But obviously, not every cycle would update all 3 of them. So you have to somehow homomorphically, signal that this particular update is valid, because everything is encrypted. You have to execute everything. All these three boxes will be executed all the time. Only one of them would be updated, and that would be updated, and that sort of is taken care of by a signal. Okay. So coming to the most expensive parts of this VM. You would notice that in this entire schematic, there are things called CBT. Like this. This is a CBT. And there are many of them. And this thing stands for circuit bootstrapping. And I would say that this and the RAM forms the major component, like major time component of the entire VM. And surprisingly, to be very honest, we were not expecting this before, but after developing, we realized that the entire VM uses this one core routine called circuit bootstrapping entirely. And if you're able to accelerate this particular core routine, you'll be able to accelerate the VM a lot. So what is circuit bootstrapping? Well, how many of you are familiar with GLWE ciphertext? Okay, cool. So what is a GLWE ciphertext? Well, GLWE ciphertext is a form of FHE ciphertext, I would say. You can do things with it, but it does not necessarily need to be FHE ciphertext. What needs to be done in circuit bootstrapping is that you send a GLWE ciphertext that encrypts a plain text, K, to a GGSW ciphertext. GGSW ciphertext is, a bigger, think of like many GLWE ciphertext. You need to send a GLWE ciphertext to a GGSW ciphertext that encrypts X to the power K. That's one variant of circuit bootstrapping. The second variant is like you just send GLW ciphertext to a GGSW ciphertext that encrypts K. Okay, these are the 2 core routines that happen, and that sort of like that comprise of the majority of the VM. And the second thing is the RAM. Okay, the problem with RAM is that since the memory is encrypted, at the moment there's no practical way of having anything better than linear cost. So if you want to retrieve an element from the RAM or write to the RAM, you have to pay for the entire RAM. You have to mutate the entire RAM at the end of the day. There are results that sort of like, make this better with some pre-processing models and so on and so forth, but those results have big constants. They're not practical. Okay. Right. Okay, so we have I would say, pretty efficient construction for RAM. As you can see, the size, the runtime for write to the RAM increases linearly with the size of the RAM. Over here, if you look at the plot over here, a 4 megabyte RAM takes a write to a 4 megabyte RAM takes around 100 milliseconds. So the VM is, the RAM is not the dominant cost for reasonably sized RAM, but it will become a dominant cost if you have like, a gigabyte of RAM or like 16 GB of RAM. If the RAM of the VM, if the RAM used by the program is small enough, let's just say, 10 megabytes, then circuit bootstrapping remains the dominant cost. Okay. Cool. So what's the performance? At the moment, it only runs at like 1.5 hertz on 32 cores. And now you may be wondering, this is pretty slow, and that's true. Are there any hope for improvements? And I would say yes. Okay, so what are the hope for improvements? Well, first, how many of you are familiar with FHE? Like engineering in FHE? FHE is embarrassing and parallelizable. You can parallelize FHE circuits very well. And we expect that we haven't tested on like 256 cores. We've only tested up to 64 cores. The performance doubles with every doubling of the cores. So if you go from 32 cores to 256 cores, it would essentially double by every time. So 1.5 would go to 12 hertz, right? So by adding more cores, you can essentially speed it up. But even 12 hertz is not enough. Then you can use hardware acceleration. In practice, I've seen that GPU acceleration sort of like shaves off 2 orders of magnitude. So it gives you like, to performance, it improves by 2 orders of magnitude. So you can expect the performance on a GPU to be 1 kilohertz. But if you go to a FPGA, then it would, add another 0 to the performance improvement. Perhaps you would get 10 kilohertz. Now the question is, will we ever get into megahertz? I don't know. But seems like there are few improvements that we can make. First, as I said, CBT is the only routine that is used in the entire circuit of the VM. So if you implement CBT directly on hardware, instead of implementing it as composition of FHE routines implemented in hardware, you would definitely get more boost. See. In my opinion, if you were to do it on hardware, we would implement CBT, and we can expect much better performance improvements than just 2 or 3 orders of magnitude improvement. There can also be algorithmic improvements. For example, if you're a researcher in the room, try to figure out how to do better CBT, that is like better bootstrapping at the end of the day, how to have better RAM, and how to have better arithmetic circuits as well. By arithmetic circuits, I mean circuits for multiplication, division, as all of us know, is pretty hard in FHE, or addition and subtraction. And with that, I will end. This is the QR code to the Phantom GitHub repository. It's under permissive license. You can sort of use it, fork it, whatever you want to do with it. It's built using a Pulpy library. Pulpy is a library which is quite fast, I would say. It's again under permissive license that you can use and fork whatever you want to do with it. Thank you.
Thank you. Very interesting. I was wondering about encrypted program and encrypted data. I assume that it should be encrypted with the same secret key, right?
Yes.
If so, could you just provide some use case that you find more interesting where I need to have encrypted program with encrypted data and that will be encrypted with the same key? Some use case for it.
Think of a smart contract where you have hidden the secret key. And for example, if you receive a smart contract and you want to hide a secret key inside the smart contract.
Okay, Thanks.
Like, just to sort of iterate on top of that, it's if you're able to do that, it's essentially obfuscation with threshold assumption. And that opens a lot more use cases.
Thank you for your presentation. My question is about our expected optimization by GPU and FPGA. So do you have any concrete reasons that you expect our FPGA provides, I think, 10 times our throughput compared to the GPU?
Yeah, I mean, look at the papers. The FPGA provides much better performance than GPU in general.
So like our
and it's not true for schemes like CKKs, but it's true for schemes like Few and TFHE. That FPGA is much better because you can isolate the memory because the bootstrapping keys in TFHE and FHW is like smaller. You can just put it on the chip. It's not the chip in the memory of the FPGA, and you do not have to pay for the communication cost from the processor to the FPGA.
Thank you.
Yeah.
Is this possible to use for AI, private AI, to protect user data and AI inference?
I wouldn't suggest you to use Phantom for it, but you can use Pulpy library using which Phantom is built for encrypted LLM execution. We haven't built it, but there's no reason why one cannot do that. It supports schemes using which you can sort of like build encrypted computation on encrypted LLM evaluation, if you wish to, or AI evaluation.
Thank you.
Okay.
Oh, thank you. Where's that? All right. Hi, everyone. Can you hear me? Yeah, I guess so. So today we're going to be looking at some practical examples of building with FHE. I'm Alessandro. I'm part of Gnosis Guild, and we're building Enclave, which is an open source protocol for confidential compute. This is going to be mostly from an engineering perspective, not heavy math concepts, just some lesson learned and stuff that we built, which we think is quite interesting and useful for the future. So just some sort of background. Why do we think this is important? Today, there's a lot of data that is used, that is sold, and people profit from it. Like Facebook, Google, these corporations, they can profit from your data. And what do you get in return? Sure, you give your data in plain text, you access certain systems, you get the benefits, but what if it be possible to actually control your data, keep it private, and still benefit from such systems? If you do choose to opt out from these systems, of course, like there is less collaborations, and even stuff like AI models, they might not be trained on all the relevant data as well. So this kind of brings us to more collaborative ideas of building. And some of the examples of like confidential collaborative compute would be like medical research, which is usually like a hot topic for FHE. How can we collaborate on analyzing data and keep it private? Private voting is just a very simple use case, which a lot of people are trying to solve, and as well as auctions or like training AI models. So we look at this trilemma. Basically, a lot of the applications that are built nowadays, they sort of like give 2 out of these 3 properties, and we think that without a combination of FHE, ZK, and MPC, it's kind of hard to get all 3 of them. You might get confidentiality and verifiability, but you sort of lose on aggregation. You might get confidentiality and aggregation, but then you lose on verifiability. And basically, we can see how confidentiality can be given by FHE, MPC gives us collaboration, and ZKP gives us the verification. So we built Enclave with the goal of solving this. And basically, we want everything. We want people to collaborate on compute, on any sort of like use cases you might think that is possible, and which not all of them might be possible at this moment, but as stuff improves, we'll be able to get more and more complex programs. We want everything to be verifiable, and we use CKP for that, and that's really important for our systems. And we don't want any of the inputs to be revealed at any time, just a sort of output from the FHE computation. This kind of sums it up in a graphic way. There's a bunch of people bringing the plain text inputs. That gets encrypted with a key from the network for the computation. There's some sort of compute, which is done confidentially on this data. And then there is an output. This output is encrypted, and then it will be decrypted by a threshold network. Once we have the output, then, of course, a lot of new things can happen. But as you can see, like, we don't want this sort of input to ever be decrypted. Okay, let's look at a very simple example. And one of the first things we built at Enclave, on top of Enclave, is actually voting. I think it's a very simple use case. Everyone understands it. And without FHE and PCNCK, it's kind of hard to sort of get it right. So some of the properties we want are having secret ballots. So just like traditional voting systems, your vote should be kept private. We want it verifiable, which is something that traditional systems don't really give you. We want to have receipt freeness. That is sort of to prevent collusion and coercion. And finally, we want to distribute trust. We don't want our secrets to be revealed. And for that, we need some sort of distribution of the trust, which in this case is the key used for encryption and decryption. Some of the technologies, we decided to go with BFE. So when Enclave started, we decided to use BFE. That gave us access to some very efficient addition, and for voting, that's just all we need, really. Thinking of TFHE is a bit overkill for that. We want ZK for proving that your ciphertext is valid, proving that the tally is valid, and that your vote is valid and fits within certain constraints, as well as being able to sort of vote anonymously. And then we use threshold cryptography for the sort of trust. So there is a network of nodes which hold part of the key, and that key can be reconstructed with a threshold. And the premise is that they will never decrypt the input. And we do have some sort of like game theory and financial incentives to prevent that. So yeah, like just a simple thing. So taking as an example, like on-chain governance, you usually have votes that are like yes, no, maybe you abstain. Some might use it, some might not. But at a simple sort of case, we take just yes and no. The cool thing about these BFE schemes is that it works on polynomials. And let's just take a polynomial of degree 10 and like flatten it out. Like let's get like an array of 10 elements, and we arbitrarily choose that the first five indexes are for yes, and the last 5 are for no. So we can efficiently encode a certain vote. Of course, with a degree of 10, you're not able to get a large vote in that, but in reality, for production use cases, you'll have much larger polynomials. In this case, like we just take 10, we take the first 5, so it's 0 times 1, 1 times 2, and then 4 times 2. We get a plus 2 equals 10, and 0 for the no. Imagine it's like all the people come in, they encode their ciphertext, they encrypt it, and it still has a flattened array. And then there's some sort of FHE computation done on that. So all of these indices are summed. And then let's imagine we get to this sort of tally. Then we take the same sort of formula. The first 5 are yes, the last 5 are no. Clearly no is 0 in this case. And then we just like reconstruct the part for yes, and we get 18. This is highly parallelizable, so that's pretty good to get done fairly quickly. But of course, like this is super, super simple. In reality, the sort of degree that we use in production can be up to like 8,192, which is like a large polynomial. So how do we add receive freeness then? Then here we start combining ZK into it. Basically, we want a circuit that people can use to either like prove that you're a voter or prove that you're not a voter because you can't reconstruct, you don't have basic access to the private key of the voter, but you're doing some sort of masking operations. So when you encrypt like a ciphertext of 0, due to like random noise and errors, you always get like a different ciphertext. So to externalize a ciphertext of 0 is not really, it's different from, I mean, two ciphertext zeros are different. What if you can actually take the previous vote of someone and just add 0 to it, and you get a completely new ciphertext, some sort of refreshing the ciphertext, basically. And because everything is done through a ZK circuit, this sort of like authentication logic is masked away. And to an external eye, you wouldn't know if you're actually voting for the first time, if you're overrunning your vote, or if you're actually just adding 0 to it. So with enough honest parties, you can actually get receive freeness because you get plausible deniability that you voted in a certain way or that you haven't voted, for instance. Yeah, just went through this. Something quite important there is that because we work this with encrypted data, we want it to be, we want to ensure that this is encrypted correctly. So every time a user sends an input to the system, we use a tool called Greco, developed by PSC, which we ported to Noir and adapted for certain other use cases. But basically, like, it takes a plain text, it takes a key, it takes a ciphertext, and you need to prove that this ciphertext is the derivation of the plain text with this key. Because there are sort of like economics involved in the system, if users were able to just send like random ciphertext, that would sort of break the system down, and nodes would get slashed for not really the fault. But the issue with this is like it's quite computing intensive, and that maybe sort of brings me to some other sort of rant about building with FHE, is that we get like very large ciphertext, at least with BFE, and proof for like validity can be quite expensive. Just to finish the flow of the voting, each of the person will submit the vote, the proof, whether it's a vote, whether it's a masking, we don't know that. All of the votes are then summed up, and we basically get the tally. Then the tally is decrypted by the threshold network. Just a sort of representation of that. We see user come, they put a private key, sort of private key in a balance. We check, okay, do you have the right private key that results into a leaf within the tree? Cool, if you're that sort of authenticated users, then your vote can be an encryption on anything, as long as it's within your balance. But if you don't pass the authentication steps, then we need to check within the circuit that the actual ciphertext you bring in is an encryption at 0. And that adds a lot of constraint to the circuit. And then, again, if you are just masking, so adding 0, we also need to prove that the operation you're doing, and we need to prove that within the circuit, is that just the sum of the previous ciphertext with 0. Apologies for the resolution here. It's probably a bit hard to see, but I guess you got the gist of it. And finally, for the distributed trust, there's no single node that can decrypt the data. Sure, they could be colluding between themselves and decrypting the data, but that sort of brings economics. They can basically just get slashed. And they, of course, don't want that unless the sort of reward for doing the early decryption or disclosing data is higher than the reward they get for behaving honestly. The thing is, like, for this to work, we sort of want a verifiability at all steps. So it's not just about the voting or the FHE computation itself. It's like, how do we ensure that the key used by the network is actually correct? We use a publicly verifiable secret sharing and a distributed key generation ceremony. So for each sort of computation, there's like a ephemeral key. So like the nodes, after the computation is done, they can just forget about the key, and there's more security added to it. But the issue is like they need to perform some sort of MPC. In this case, we do it in an interactive way with a low bandwidth. But basically, you need to like generate a key pair, you need to like share it, and you need to You need to encrypt it as well, send it to others, they can decrypt it, and then start forming this sort of key that the network uses. And that's quite intensive. We tried going through some implementations. Our cryptographer will know better, but there was implementation about publicly verifiable secret sharing. They were suggesting to use PVW encryption. We spent a few months on that, and the ciphertext ended up being like huge. The engineers working on the nodes were like, right, this is going to be a bit tough. We're sending like a huge amount of data in the network. This is just not going to work. So what we decided to do instead is just reusing BFE. And while we use like we use threshold BFE for the actual FHE computations, we can just use normal BFE for encrypting the share. And that was kind of sweet for us because we had all of this stuff already built in. And at the same time, we having the circuit for verifying the ciphertext encryption, we can sort of adapt this circuit for verifying that the encryption of the share, the aggregation, and then eventually the decryption of the tally of the output is done correctly. So yeah, there's a lot of trade-offs in here. Like if we want to achieve a higher level of security, which is like at a minimum 128 bit to get post-quantum security, then we need a very large parameter set. I talked before about the polynomials being 10 degree for that example, but to some of the parameters we tried working with, we ended up having a polynomials of degree 8192, which is massive. And verifying all of these, it's very intensive. Like as of now, for a user to verify the ciphertext with this level of security, bear in mind that we're also ensuring that the network is enough distributed. So we also raise the number of parties that hold the key. And yeah, this basically brings up to like a huge number of constraints, which because the user need to do this on the browser, they come and they encrypt the data and they prove client side. We might, we get into some troubles where like, sure, formula constraint is not really going to work on a browser now, so we're working towards some optimizations, or at least for the time being, for demo purposes, working with smaller parameters. Some other, of course, options would be just using proof delegation, but we haven't really explored that for now. Another cool thing about BFE and sort of like the voting use case is that it's sort of lightweight. You just basically summing up ciphertext. And what we found is that because we talk a lot about verifiability across the stack, we want this sort of computation to be verifiable as well. And basically, we just run the addition inside the RISC-0 VM. You could choose other ZK VMs. And this just gets us a gross system proof, and they can be verified on chain pretty succinctly and cheaply. There's some other use cases which we explored. We played a bit with sunscreen SPF. That's pretty cool. We could build some demo for like auctions. It's just like building this into the system will require a lot of changes just because we focus on BFE for now, so integrating all the new DKG and the keys and perhaps bootstrapping as well would be like a lot of work. And then finally, because we want verifiability, sort of a questions to you guys and to people working on this is like, could this computation actually be verifiable and run within, let's say, a ZK VM? Some of the lessons learned is that this is a very exciting space. I joined like 3 months ago. I've been working on ZK in the past a lot, but not on FHE. And yeah, it just sort of like blows my brain seeing the sort of cool stuff that everyone here is building and that we are building as well. It's clear that there's different schemes. Some of them will be useful for certain use case, some for others. So it's very cool to see sort of scheme switching being very implemented, and we're very excited to try out libraries like PoolPy for that. But the goal is like, we don't want developers to actually worry about any of this. Even users, like they come, we want to run this computation, cool, this is the best scheme for that, this is a program for it, it'll just work right out the buff. And we're not there yet, of course. Yeah, so verifiability again, that's very resource intensive, and we want to see improvement on that. We're working very hard to improve, to optimize the circuits we're working on. It's just like, I've been chosen to work with Noir and polynomials. It can be a little bit tough, but eventually we'll get there. And even more like if you're adding extra sort of like logic into the circuit, that ends up blowing up. And for users to run that in their own browsers, it's not great. Another issues we face is like, because of such large polynomials and some of them needed to be public inputs to the verifier, then we end up sending a huge call data on chain. So basically we need to work with commitment schemes to just send a commitment to the data, but that sort of blows up the circuit even more because we need to do a lot of hashing in it. So there's all sort of like drawbacks in our places. But what we think the ecosystem needs is like scheme libraries for multi-scheme support. We want to see more and more libraries being improved and maintained. Verifiability seems like a very hot topic, and it'd be great if the ecosystem continues to work on that and trying to work out on optimizing circuits and primitives for proving your ciphertext encryption. Yeah, I mean, that's the end of it, really. Like, if you're interested in Enclave, please just check this out. And yeah, that's it. If you got any questions, I think we got a minute and a half.
Next, we have a panel, and it will require a little bit of physical exercise by the speakers because we have no chairs here. So all the speakers, please come up. If you're very far in the back, you can just take one of the chairs here in the front.
We have three, or are you going to be asking questions to the public, or are you going to be talking just by yourselves?
I think no public. No public.
Okay. And this one, let me check, and this one I will change the battery real quick.
Thank you.
Wow. Do we need like introduction, or can just skip it because we only have like 20 minutes? So maybe I'll get like straight to the point. Like over the years, we have seen like, very many teams develop Ping FXG. But then, like, I think we are kind of like different in opinions in like how we develop this thing in terms of like also schemes and tooling, and also like what kind of use case that we're looking for, and like. But in the end of the day, the goal of the panel is just to let everyone, have a chance to, like share all these like difficulties, bottlenecks, experience, and then, finally, hopefully that we can agree on like some general thing to work on the next year, even if it is just like in the form of some hints. Good enough? Okay. So I think like we can start with, like a brief introduction of like everyone here. We have like, researchers, from academic. We have like developers. We also have like some like product people here, which I think is like quite representative for like the FHG builder system ecosystem, I guess. So maybe like each of you can like share your when you are developing or develop FHG, what are the difficulties that you encounter when you're building, and also like with what you're building, what are the bottlenecks, and if you are looking into like some potential thing. Yeah, we can go from like the round.
Okay. Hi, I'm Janma Jamal from R&D organization called Phantom.Zone. For short, we call it PZ. What is the first prompt? First prompt is...
yeah, so in general, like sharing like the difficulties when you build FHG.
Right. Well, I work at a lower stack, which means that I design FHG algorithms and write the I don't write circuits in general. I just write the algorithms. The difficulties that we face. Well, it's very hard to interoperate with hardware people. As someone working on algorithms, it just there's no codem for interfacing with people doing hardware acceleration for FHG. Hopefully that improves in the future. In terms of if I were a developer, I would say there doesn't not exist standard library like the way it exists for ZK. There's no way to reason about, like, for example, in ZK we have custom circuits, we have Plonkish circuits, and so we have air arithmetic. That doesn't exist in FHG space. It's just very hard to navigate the space if you do not have that.
Yeah, hey, I'm Alessandro. I work in Enclave, and I work at a higher level than Jamjaya, is that right? Yeah, sorry. And yeah, I mean, some of the difficulties, personal level is just like getting into the space, the FHE is like, there's just so much to look at. Some of it can be not properly explained, so sort of like education as well is very important. Like having like more accessible blog posts, like papers sort of deciphered, more examples. That would be really useful for like people just joining the space. And in terms of like when building with it, for sure, like the lack of like general libraries and sort of an abstraction layer, I feel like that would make our life much, much easier. And especially like what I mentioned in the talk is the ZK part of it. Like we need ZK for FHE, like it's mandatory, but the sort of like, it's the bottleneck, at least in my opinion, of getting your computation verifiable and anything around the stack.
Hi, my name is Eugene. I'm from Ethereum. Some problems. The most problem I faced throughout this week was educating people. So people now, they have heard about FHE, but they don't even know what FHE means. So I spend a lot of time to educate people about what it is and what problem we can solve, kind of things. So that's one thing. Another is, as they mentioned, I also feel like the need for standard of more what would be the best way to make a standard and then share that so that we, the application layers or some consumers, they don't get confused when they want to use FHE on Ethereum. And also, there are other technologies that try to achieve the privacy. And so there are many different technologies. So how do we work together to make it more clearer for people? So explaining in more layman's language would be very important. And yeah, that's my opinion.
Hi, my name is Gurgen. I'm from Fairmass team. And when we talk about challenges, I think we need to separate or consider general two main groups: customers of the technology and developers. If we talk about customers, I think it's general problem about privacy. We need to provide some real use case, scalable, not just private transfers, private tokens, but show that we really need privacy, because we have some hype on privacy. We talk about privacy a lot. But when you started to talk with crypto banks, with some DeFi companies, all of them wants to privacy, but right now they have a lot of customers and they can make money without privacy at this stage. And all of them say, yeah, we need, but probably a little bit later. When we talk about developers, the problem we started with was we started to build application layer for developers, because building applications for developers is very hard right now, because it's now looks like you are building applications as a developer on assembler language with very limited operations. This is the one thing we are trying in our team simplify. Another thing, again, I talk about a lot, we need to find the way how to combine different technologies together, how with FHE to organize joint computations. This is the biggest problem from my point of view, because it needs us to use ZK, to use MPC. It's that's much harder all stack with a lot of bottlenecks, with a lot of hardness and degree security.
Hello, I'm Tom from Phoenix. The main challenges that we see are essentially three. We want to make privacy and encryption seamless for developers. We want to make privacy and encryption seamless for users. And I think both of them, to some level, we achieve with the coprocessor architecture. This is definitely something like we can, further improve on. It's still not perfect, and I don't know if the coprocessor model will be like the end game for this. This is, I think, something that is like very suitable right now with the tools that we have now. I don't know if this is the end game, but this is like definitely two angles that we really want to like focus and improve on. And the third and last one, maybe the most important, is performance. And here again, like this is on one end the performance of the computations themselves, on the other end is the performance of decryptions. Something that people often forget about is that any data that is encrypted and computed over encrypted in an encrypted state needs to be decrypted eventually, because people open their wallets and they see the balances of all their tokens. And this is something that we need to improve performance on as well, because as we get adoption, as we get like thousands of users, we get a lot of decryption requests. And since FHE caters towards mainly private shared state versus single users, private shared state versus single user privacy, this is something really important.
Hi, I'm Kiwoo. I'm from PSE, and I'm more of a cryptographer. I'm on the academic side of FHE. I did my PhD in FHE and spent 2 years as a postdoc, and has recently joined PSE as a researcher. One difficulty, I saw people facing was like because of this FHE has very unintuitive cost model. Like when I was like PhD student, like a lot of for example, from people from biology or like control theory, reached out to our lab to collaborate on several projects, but they were like, why can't we do this in FHE? Like for example, like RAM model, like the if statements or the while statements, and they just had difficulties understanding what's efficient under FHE and something is not. So they sometimes bring us some. They built some FHE circuit, but like no, that's not the way you can do it. Like that's gonna be like too inefficient, and yeah, this kind of weird cost model kind of hinders the adoption and makes the difficulty for the developers and user ends, I think.
So I'm Clément. I'm working for Zama for a few years now, and I'm working mainly on the blockchain part. And I feel like we have two kind of challenges. Like we have the more crypto primitive, so someone mentioned the proving execution, which is really important and still something where we are doing research also. But I feel like something which came up when you have a more mature technology is to actually build a product. And I think this is like a big challenge to realize that what would work for developers, because we all know that privacy is not the most important thing for many people, and if it's too hard to implement, like people will just drop the feature. So you need to be better than any other features, because it's not something people consider a lot. I think like it's good, like we have a privacy season, so like many people like take care of that right now, so this is great. But we need to go beyond that. So it has been already mentioned by Tom, but I totally agree that we need to push further about that. The composer approach is clearly a good one to drive adoption, because people can just write Solidity code. But is it the end goal? Can we do better? Can we do like more to drive the adoption for that developer? I think we need to continue on this road, on tooling and everything.
Yeah, so thanks everyone. So I'll try my best to make a summary like out of these like 7 opinions. So we face, first of all, so let's say that we agree that FXG is a technology, but it is not a solution. And we need to work harder to make it a solution, right? And then we engage like different kind of difficulties when we try to use this technology in privacy solution. Let's say that first, like there is a lack of introductory material for new beginners that try to get into this FXG for privacy. And then second, there is a gap between the traditional programming model and programming in FXG, right? And third, actually like approaching from the perspective of a privacy solution, let's say product builder, they have a hard time to understand what can they do with FXG if we don't have like let's say a good tooling or a good stack using FXG for them. So like all these, of course, we also have like problem with trying to like increase the performance of FXG, which is like the core of the whole thing. So like, but these are like like the parallel fronts that we can work on, and I believe like each of you here are already like engaged in one or more aspect of this and trying to improve this thing. Okay, so I'll tell you like ahead that after the next question there will be a voting, okay? But then you can have like try to think about like whether you vote for it or not, like when you are answering the next question. Verifiable FXG and FXG, okay? Practicality. Whether you believe or not, in 3 years we have practical FXG and verifiable FXG. Oh, no, hold on. You have time to think. Slow down. But then, that is like, you don't have to explain. Just vote, okay? We just like want to. Like,
I just voted.
Yeah, right. But the next question is like, what do you think about the current key management of FXG-based solution? We can go like this.
What in particular about key management solutions?
Oh yeah, like in almost like all current privacy solution using FXG, we have this centralized key. And how do we manage this? The decryption key.
It's not centralized. It's threshold, right?
Oh yeah.
Okay.
Right, but I mean like one key for everyone.
Oh,
yeah.
Right.
Almost centralized.
Yeah. If you do not, almost centralized. Yes. So what is the opinion of our?
Yeah.
Oh, I see.
Like we are using this, but like, is it okay? What are the awkward feeling when you kind of like center your privacy around this key?
Okay, I'll go first if that's okay. I think that it depends on the context. Like, in what use case are you deploying the FXG system for? If you're saying that there's a blockchain and it's like as trustless as Aztec or as trustless as Ethereum with FXG threshold decryption, that's false. That's not true, because if you can leak the secret, and someone will bribe you and leak the secret, and that's not attributable. That you cannot design economic incentives unless something is attributable. But if you are able to design spin up a system where you have legal contracts with the other party and you have threshold systems who have legal contracts with everyone, then everything is fine. Because you have legal contracts, there is a particular thing that enforces the entire system to not be bribable, and that's fine, in my opinion. Oh.
I have one.
Essentially, most of the use cases for the decryption committee, or like the MPC protocol for threshold decryption, is for us to have private share state, again, in comparison to a single user privacy. And so you can build protocols like Railgun, like privacy pools, that, we can build those with FHE as well, and have like single user privacy, or like, sort of more self-sovereign. You can decrypt only you can decrypt your own data, you're in full control and everything. The problem is that, well, unless proven otherwise, these systems always require some measurements in reality to also deal with bad actors, like hackers, and mainly actors, state actors, and malicious activity. And using, to actually tackle that, we use like, mechanisms like proof of innocence and protocols for disassociation and stuff like that. People need to wait for a day, for example, before entering the private pool in order to prove their innocence or honesty. But like, what happens if a day is not enough? Like, we saw use cases where, there were hacks and exploits where all of the addresses associated with this hack is revealed only like a few weeks or a month after. What happens then? So these technologies are not perfect for that. So this is, for example, why a committee-based threshold decryption is much more powerful to tackle that. And I think that true adoption also needs to tackle these kind of questions of like, okay, what happens, when regulators and states require the protocols to actually very specifically in a very specific use case or an instance to reveal some sort of information without like a disclosure. So what I'm trying to say is that all models are powerful in their own way. Currently seems like the MPC protocols are a bit more pragmatic and tackle the future with a bit more like a realistic approach. So they're powerful on their own.
I think there was also something on the MPC side, which is something we need to work on in the verifiability of decryption, to be able to prove that decryption is actually done correctly by all parties. And this is like, it's not like perfect, you don't solve everything. And I totally agree that for like having like legal contract with all parties is still the best solution for now. But yeah, this is like a roadmap like for the MPC to have verifiability.
Just one point. I'm speaking again, so I just want to make sure I'm not over speaking. Okay, cool. Just one point on just one thing on one top mentioned. I think the benefit of the downside of having an MPC committee that becomes this king that could decrypt arbitrarily at any regulation or state actor request, then it's not a blockchain, because I'm not given I lose. Like, if you're able to control the state for me, then it's not like I don't have right over it. It's not like my state, right? Then it's something else. Probably that's a better system as with the regulation, but it's no more a blockchain.
Right. So I think, like basically what we just discussed here is that, you know, like unfortunately we have this key that is like the problem of like, you know, privacy solution based on FXG right now. And then let's say that we have different models in terms of like how do we custody this privacy. Sometimes you can, you know, just rely on a committee, maybe a rotating one on a TE, but then there may be also like the model where you can like engage with real world actors to you know, have some post hoc resolution about this whole situation if your privacy is like at stake, or you know, someone violate your privacy in some way. Yeah, and then like obviously we also like need to work on you know, like how do we authorize access to our encrypted data on Ethereum. That is like another difficult problem that we need to add to our roadmap. Okay.
Just small comments. Is the problem only when you talk about private shared state? I mean about the key. If you don't need private shared state, it's not a problem at all.
Yes, I think we are talking about private shared state. Yes. Yeah, so like time for voting. Practical FXG in 3 years. Okay.
In 2?
Practical VFXG in 5 years.
Oh, practical verifiable FHE in
Yeah.
5 years?
5.
Probably I think so.
Anyone? Oh. That's the spirit. Okay, so I think like we have like already like surfaced the difficulties, problems in building with FXG, and we also have like let's say a glimpse size on like what we should expect in terms of you know, development of like TPS and also hopefully tooling in the. So if you have to choose like 2 to 3 problems, okay, maybe 1 to 2 problems that you have to work on in the next year, what will be it? Yeah, we're going to do a round, you know. It's not like, yeah. Maybe
no, I feel like a verifiable FHE is clearly on the pure research run really important, and also verifiable MPC. Having like the way to have more trust in the process is really important if you want to build a true decentralized system. So yeah, I would say on research this is the 2 main, and overall like performance is also obviously important. Even like we did like a huge progress, but if you want to onboard like basically the whole blockchain, let's be utopist, but I think it will happen at some point. I'm convinced we need to improve that.
so to increase the privacy guarantee when we have the central key, basically key management next year. Great. Yeah, Kiwoo?
Going a line, right?
Yeah, we are going to do a round.
I think verifiable FHE is a bit far away, but I think verifiable decryption we can work on more. Like Phoenix did published recent paper, and but it's not like publicly auditable. It is like maliciously secure, but we can also work on like publicly auditable, verifiable decryption. I think that's one thing that we can work on.
Okay, proof of decryption, publicly verifiable.
I would say 2 things, right? So performance, definitely. And I think one thing that is often neglected is developer tools and user experience tools to kind of bridge the gap. It feels like currently FHE-based systems are more for like power users or advanced users, and it's really not the point. Like we want to actually, you know, for it to be approachable for everyday users. So yeah.
Great, thanks. So that is on developer experience.
Developer experience, user experience, and performance.
That's 3. Yeah, please.
For me, a couple of directions. The first of them is find a way to build new FHE schemes fully new way, because all schemes that we have right now, they follows the same idea based on the gentry's work with bootstrapping. All of the schemes, practical and secure scheme, follows the same idea more or less. Another thing, joint computation. If we talk about decryption, threshold decryption protocol, we don't know the way how we can eliminate this part, at least right now. But if we consider the way to use threshold decryption protocol, we need to find the way how we can build scalable threshold decryption to be able to have thousands of nodes in the decryption protocol. And there are two parts in threshold decryption protocols. One of them is decryption, let's say, part, where you decrypt. Another part is when you generate the key. It's probably two different parts, but all of them responsible for scalability. And the developer experience also are one of the important parts.
I want to talk a little more real-world use cases. So personally, AI changed my life a lot this year, and I see that the advancement is really speed up. And AI they develop by consuming our humans' data, and then we don't get any benefit out of it. And now Google is building world model, and then it will be only accelerating. And I always think about how can I protect my privacy, and how can I get benefit out of the AI consuming my data and learning from it, so that they will eventually replace humans, and including myself. Then maybe we can use FHE for protecting our data, and then get some incentive out of for their using our data. And the incentive schemes and the protecting and then usage, all these usage can be done by using Ethereum as a settlement layer, and also using the privacy preserving this FHE tag. So I am very passionate about in these real world use cases. Currently we only have the FHE as a tag, but we want to find a way to build these use cases, how to use our tag.
For me, I would say focusing on the ZK part of FHE, so the verifiability. I feel cutting the cost of proving down and optimizing that would be what we focus on, and that would be really useful for the ecosystem. But in 1 year is probably not enough, but we need to get started. And on the other hand, of the spectrum is the developer experience. There's so many cool stuff we can build with it. It's just who's building it? There's not enough developers building it just because it's, there's no documentation. There's libraries that are a bit clunky. It's just everything is fragmented. It's not properly explained. And trying to get everything in a place where it becomes easier for people just, go to a hackathon and build stuff and take it from there, really. Right. 3, right? 3 or
1 to 2.
1 to 2. I see. Just before that, one point on new schemes. I think there are a lot of good people working on code-based FHE systems, and there's a new paper from Rabital Technologies about graphene. I think there needs to be more, speaking about new schemes and FHE conference, you laughed at. But I would say that there needs to be more encouragement about building new FHE-based systems that do not rely on lattices, because we do not want to be putting everything into a single bucket. Okay, now the first thing that I would want to work on, or I would want others to prioritize as well, is it's inevitable that we would see deployment in blockchain context and decentralized settings in a co-processor model. I would say we should try to minimize the surface area of attack. There has not been much discussion about, all of us are essentially trusting these MPC committees. We should try to design systems and the way they interface with the actual smart contract in a way that the user is not drugged for privacy or even for state by a state actor in certain settings. Or not even state actor, probably, there could be someone else bribing, someone sitting in, Serbia bribing people and sort of that's drugged. And legal contracts are a good way to do it. The second thing that I would say
is work on probably we need to see more applications that are not related to private shared state. I mean, there's one really good application that I would personally pay for, oblivious message retrieval, that one should work on. We should be try to solve PIR and make it concretely faster. PIR has this issue which all of us know it's really runtime, but they need FHE sort of like is really good in settings where a person holds their secret key and it is sort of like offloading of a heavy compute to a beefy server. And there are a lot of use cases for in this blockchain space. Probably not, deploying private shared state. Private shared is one probably commercially viable use case. Probably there are the use cases where we can use it for. Yeah.
Wow. So, yeah, I think I'm glad that we, kind of join together today here, share our opinions, and also share what will be prioritized to work on the next year, and hopefully that after this we can kind of make an open research forum where we can if you're working on verifiable decryption or a model to do key management, or working on improving the user experience, developer experience, then you need access to hardware, builder, and yeah, I think this is maybe a good chance to join Fox and do something and move the whole FXG forward. Not just something exists only on design, but then we actually have applications in 3 to 5 years. So thanks everyone.
Quick plug, after the lunch break at around a little bit before 2 p.m., we will have obfuscation day here. If you haven't registered for that, there may still be space here. If you're interested in that, just pop up. If it's not full, you can come. So yeah, it will be interesting. Okay, hi everyone. Thanks a lot for joining the obfuscation day at Devconnect. We have a small technical gathering here, and the goal was to just bring together some people that are interested in building in this space and just want to learn more. The event here is hosted by the PSE team from the Ethereum Foundation. We will have 3 talks, each half an hour, and afterwards 1 panel. Yeah, and then afterwards will be the closing ceremonies at Devconnect, I think at 5 p.m. So we will end here at 4. You will make it well in time to the closing ceremonies. If you hear something interesting, find a speaker later. If you're looking for collaborators, it's a great place to say so here. You can also catch me in the back if you have opinions or thoughts on what the Ethereum Foundation or PSE should do in this space. Yeah, thanks again for being here. And so let's get started with the first speaker, which is Sora.
Can we start from now?
Yep, can start now.
Okay, hi everyone. Yeah, thank you. So thank you for joining this obfuscation day. So I'm Sora from Magna.io, a project within Ethereum Foundation, PSE. So today, we'd like to challenge 2 common beliefs about IO. Where is IO would be nice to have, but it isn't strictly necessary for most applications. And the second one is IO is technology that's still 10 years away, and we don't know any path toward practical IO. So how many people believe these 2 arguments? Thank you, cool. So in the first part, we show that IO is essential for enabling confidential smart contracts in a scalable way for Ethereum. And in the latter part, we'll present our roadmap toward practical implementation of IO. And actually, we only have 3 technical components that we don't know how to implement practically. And if we can implement them, we believe we can extend them to our practical IO construction, as long as the assumptions for our IO construction remain secure. Okay, so before going to the first part, let's review the history of how Ethereum have improved scalability for public smart contracts. Oh, I think design seems to be slightly broken, but like that's a not big problem. So the vanilla Ethereum without any programmable cryptography, without SNAC, was not scalable because validators need to perform all the M computation to verify M transactions per second. And this problem was temporarily solved by sidechains. So transactions are processed by sidechain committee, which is different from the Ethereum validators. And only some commitments of sidechain blocks has been recorded onto the Ethereum layer 1. However, this next introduced security issue because that sidechain committee is less decentralized and less secure. And finally, ZK Rollup appeared. It requests a trustless, permissionless prover to generate a proof of the M transactions. And the committee only need to perform constant communication to verify this proof. And this solves the security and the efficiency scalability issues at the same time by delegating such heavy linear part computation to our permissionless parties, and then keeping the validator's computational cost constant. Then how about scalability for confidential smart contracts? So vanilla Ethereum definitely does not support confidential smart contracts. And even with ZKP, we cannot support contracts that involve multiple users' private inputs. And this problem is addressed by one solution for this problem is FEG plus MPC for decryption. So it introduces an MPC committee to perform decryption, to decrypt ciphertext of output from confidential smart contracts. And this can be compatible with this does not require any new tasks on the Ethereum validators, since every work is done by this committee. So this also implies it introduces a security issue, since users need to trust this MPC committee, which is also less decentralized than the Ethereum validators. We can place I/O as a solution that solves the security and scalability issue at the same time, but for confidential smart contracts. Some people might think it's still possible to modify Ethereum protocol to have validators support this MPC decryption for FEG. But we don't think this approach works, because this introduces a significant trade-off between the security and the scalability. So let's consider the case where the number of the transactions per second for confidential smart contracts increase in double. And since the computational cost and communication cost for each committee party increases in the same order, the committee party need to increase their computational and communication throughput of their hardware in the same way. But this worsens the decentralization of the committee parties, because only rich people who can operate high-performance computers will be able to join this committee. And also, this worsens the geographic decentralization, since they might be able to operate with enough network throughput only in regions with high network bandwidth. In this way, we believe I/O is a necessary solution to solve this trade-off between security and scalability. And to give up on practical I/O today is equivalent to having given up on practical snack in the past. Okay, so then let's go to more deep part of the construction. So I have not explained what I/O is actually. So I/O can be seen as a program compiler. If you have some program which makes some output on some inputs, you can make an obfuscated version of the circuit by using I/O. And while this makes the same output, as the original circuit for any inputs, this obfuscated circuit intuitively ensures that you cannot get some secret within this obfuscated circuit. And in practice, we can consider one obfuscator who makes some circuit with some secrets, and then makes the obfuscated circuit and distribute it to the publicly. And then any evaluator can evaluate this. Any user can download this obfuscated circuit and evaluate it on any inputs without interacting with this obfuscator. And you might think, in blockchain use cases, we cannot assume such single trusted obfuscator. So in practice, we can also consider I/O obfuscation with decentralized parties. And in this case, and also in the blockchain use cases, we don't need to hide all of the functionalities. Rather than that, we only need to hide some hard-coded secrets. So we can, in this obfuscated, decentralized obfuscation, participants will provide their own secret key, and by doing some MPC, they can make an obfuscated circuit such that as long as at least one party is honest, no single party can know the final hard-coded secret within this obfuscated circuit. And have you ever received our position paper? Yeah, we are distributing real paper. And more concrete technique to make this obfuscation decentralized and make this process verifiable are explained in this paper. Okay, so, and formally, there are two security definitions of I/O. So one is indistinguishable obfuscation. I think this is more famous. And but actually, this only guarantees that, or this does not guarantee that any secret within the obfuscated circuits remains private. But it can be constructed without any heuristic assumptions, at least theoretically. The other assumption is ideal obfuscation. This ensures that the obfuscated circuit does not reveal any non-trivial information beyond its input-output behaviors. However, it is known that we cannot make such ideal obfuscations for any programs without any heuristics. But in other words, if we introduce a heuristic model called pseudo-random oracle model, we can actually construct this for most of the natural programs. And if we have indistinguished obfuscation, we can easily extend this to ideal obfuscation by combining hash function. So in the following, when we use I/O or as like a tool black box, I will explain the security based on the security definition of this ideal obfuscation. While when we talk about how to construct I/O, this I/O means indistinguished obfuscation. Okay, so then how can we concretely make confidential smart contracts based on this I/O? And actually, instead of we make such contracts using only I/O, we also combine FEG, and this allows us to use only single implementation of I/O for any application, and we call this single implementation root I/O. So before explaining this root I/O, I'll explain the previous idea to construct confidential smart contracts based on FEG, which is basically inspired by the Xamarin FEG VM protocol. So there are three components. The first one is our smart contract on blockchains. And there are two types of the smart contracts. One is our application contract, which defines what kind of program should be homologically evaluated by FEG. And this also defines a decryption policy of the ciphertext. And the second one is a gateway contract, which orchestrates users and the other components I'll explain next. And next component is a FEG coprocessor. So this process FEG evaluation of the requested programs and the requested input ciphertext, which is specified by each application. And this is actually operated by our permissionless and trustless evaluators. And the remaining one is, last one is decryption coprocessor. So this is one of the biggest, most insecure part in this architecture. Because while this performs our FEG decryption, if the application contract confirms that this given ciphertext can be decrypted based on their decryption policies, this decryption is instantiated by the T out of an MPC committee. In other words, new trusted parties different from the Ethereum validators. So today, when we use this FEG plus MPC for decryption construction, we still need to trust this this committee to perform MPC for decryption. So our idea is we use I/O just for replacing this decryption coprocessor. And in particular, this obfuscation for this circuit function is sufficient to replace decryption coprocessor in this FEG VM architecture. So you can see that most of the parts seems to be agnostic to any of the application logic. But you also might think, while decryption policy can be different for each application, we need to fix some single verification logic to verify this given proof inside this obfuscated circuit. So how can we design such uniform verification logic? We achieve this by using gateway contract. this absorbs the difference between application-specific decryption conditions. So, for example, if there are two applications using FEG-based confidential smart contract, each of them will check if the given ciphertext satisfies their own decryption policy, application-specific decryption policy. And if this confirms it satisfies their policies, this ciphertext is provided for the gateway contract, which is a single contract for all applications. And this gateway contract will just check that the given ciphertext is legit for the caller smart contract, application contract is legit for the provided ciphertext by seeing some access control list. And if this is true, this gateway contract will output a message like, this ciphertext can be ready for decryption. And if we rely on this gateway contract, we only need to, the obfuscated circuit only need to verify that this gateway contract approves decryption for the given ciphertext on the Ethereum. So we only need to make a snag proof such that there is a event such that this gateway contract outputs the given ciphertext for decryption as a decryptable ciphertext. And this is why we only need single implementation of the obfuscated circuit for all applications. So let's summarize the idea of this FEG plus root IO. So from the perspective of trust assumptions, obfuscation process can be decentralized among an n out of n committee. And this is only for one-time setup. And you might think this still depends on some committee for MPC. But this assumption is significantly weaker than our previous ones, because if you only need this committee only for setup phase, you can easily set the threshold to the highest one, which is n, number of the committee. Because if someone goes offline and some MPC for setup fails, we can just restart the same MPC, since there's no kind of state and there's no effect to the users, since this is a process only in the setup. And once this setup is done, no additional ongoing trust assumption is necessary beyond Ethereum validators. So in this sense, we believe this FEG plus root IO is the best solution to make Ethereum really scalable and privacy preserving without sacrificing the security. And from the perspective of on-chain cost, so in the paper we show that so we can verify our outputs from the obfuscated circuit just by checking some signature. So on-chain contracts only need to perform snag plus signature verification plus some tiny public operations like access control checklist. So we can say on-chain cost for confidential smart contract in our approach can be almost as cheap as the cost for public smart contracts. Okay, so yeah, so in this parts, I assumed we already have some super practical available IO construction, and I use it as a black box. But as you know, the biggest problem is, can we make a practical IO? And this is a benchmark of our IO, lattice-based IO implementation. And this input size means input size of the program being obfuscated. So you can see that even for 4 input bit, obfuscation already takes around 5 hours, and evaluation takes 18 minutes. And this time seems to increase more than linearly. Yeah, so while we can always make some good cryptographic protocol, in practice, we always also have some a bottleneck for practical IO construction. So, and we have not directly improved this benchmark after we first implemented that implementation in last May. Because after we make this, we focused on more fundamental part, which is key homomorphic encoding. And actually, this key homomorphic encoding is a central, central component to improve the lattice-based IO construction. So I next go to the second part, which is about our roadmap to make IO practical. So this is our roadmap. So this allow with red question mark means we don't know how to implement this transformation practically. And while the allow with check mark means we know how to implement this transformation if we already have the practical implementation at the tail of each arrow. So you can see that the only missing components are homomorphic PLF over encodings, snag verifications over encodings, and the verifiable FEG. So you can find that our practical I/O is not like a kind of something we don't know, something that we don't know even the path, but it's just a complete collection of technical challenges. And in the following, I'll explain what is key homomorphic encoding and what's the exact definition of these missing components. So yeah, I'll add more like a math part, but the point is you don't need to understand all of these details. I just want to say this key homomorphic encoding is actually very simple and straightforward. So I just want to, it's enough if you can feel this is just a linear algebra and you can try to solve this problem. So, sorry, I think notation notation position seems to be broken, but we can define some encoding for integers and some secret and the public key. And this encoding is technically defined in this way, where this G is some fixed matrix, and this one is a tensor product, and this time actually also contains some LW errors. So you can see that this is very somehow close to GSW FEG ciphertext. And but it's different from our GSW FEG because it allows homomorphic property not only for this encoding but also for public keys. So specifically, we can first define algorithms such that given some circuit and the public keys for inputs, you can deliver public key corresponding to the circuit output without knowing any inputs to the encoding. And similarly, you can homomorphically evaluate circuit over given encodings without knowing secrets. But point is, this algorithms also takes as input encoded integers. And I'll elaborate this, why this X is necessary later. And this algorithm's output are encoding corresponding to the circuit output. And these two outputs satisfy this equation. So you can see that the second term contains the circuit output, but this is masked by the first term. So intuitively, if you can, when evaluator, some permissionless evaluator computes this encoding over provided homomorphically compute circuit over provided encodings, if evaluator also have access to this first term, they can obtain the circuit output. More concretely, in most applications, in most cryptographic constructions using these BZZ+ encodings, trusted party somehow provides encodings for the inputs and also this first term. And then a trustless evaluator can compute the circuit over the encoding, which makes encoding for the circuit outputs. And if this first term is also provided, these two things allow evaluator to run the circuit output. But the important point is, if the evaluator computes any not allowed circuit, like a C prime, or this output encoding will be like a different from this time, so that this S times AC pert will be different from the data provided by the trusted party. So this implies that this mask part provided by trusted party allows the evaluator to run circuit output, but only for some specific circuit. So someone might think, this seems to be like more useful than FUG, because while FUG secret key allows decryption for all ciphertext, this allows decryption only for some permitted circuits. But actually, this is not correct, because as I said, trusted party also need to send their encoded integers, because homomorphic multiplication requires the knowledge of the input integers. So that our common approach to overcome this limitation is combining FEG over BCC plus encodings. So intuitively, we encode FEG ciphertext of the private inputs and encode not the private input itself, but the FEG ciphertext. Then we simulate the FEG evaluation algorithms over these BCC plus encodings. So more concretely, trusted party will provide the encoding of their FEG encryption, and the circuit evaluated over encoding is defined as a homomorphic evaluation of some specific circuit. And by using some technique, we can also perform FEG decryption without revealing FEG secret key, so that our evaluator can obtain the encoding of the decrypted result only for some specific permitted circuits. Then I think it's ready for explaining what these, especially these two components means. So the first component, homomorphic PLF over encoding, is a problem to compute FEG PLF evaluation. This eval means FEG evaluation. So like we want to evaluate a circuit that simulates homomorphic evaluation of the PLF random function over BCC plus encoding. And this second component, snag verification over encodings, means we want to evaluate snag verification algorithms over the BCC plus encoding as a circuit. And if we can make these components practical, and also if we have verifiable FEG with practical performance, we believe we can make practical I/O, as long as some assumptions, non-standard assumptions, remain secure. And we explained more details in our paper. Okay, let's summarize this talk. So yeah, I want to tell you two messages. So one is, I/O is not just nice to have. This is essential for making Ethereum a really scalable private world computer. And the second, the practical implementation of I/O is not a kind of distant idea or discovered from reality, not the idea from like not the idea only in some theory, but the concrete collection of technical challenges. And as I said, these challenges concretely means verifiable FEG and the BCC plus encoding evaluation for homomorphic PLF and snag verification. And I hope like we can we can challenge these three components. Thank you for listening. So, do you have any questions? Okay, so your question is like why I don't consider TEE as a solution, right? For specific verifiable FHE, yeah. For specific verifiable FHE, I think just because like we need to trust. we don't want to add new trust assumption for introducing TEE. Get what?
The gateway smart contract.
Yeah.
And if you're implementing the gateway, I don't see why anybody would have an FPGA anymore.
I see. So okay, thank you for your question. So we actually don't need to evaluate proof or verify FPG within the obfuscated circuit, but this is verified by the either application contract or gateway contract. So in more detail, when FEG coprocessor computes some homomorphic circuit, they will also provide proof of the homomorphic evaluation. And this is verified by any of the smart contract. And if this proof is verified on-chain, I expect this gateway contract will approve decryption of that output ciphertext. Sign. So why do you improve this?
So the gateway contract would check whether the output ciphertext is correct.
Yeah.
And then hash it, and then sign it. And the conditional decryptor verifies the signature somehow, and then decrypts it. How can they sign it?
What?
How can they sign it?
Oh, so the conditional decryptor only says that, I would only decrypt the ciphertext as long as gateway smart contract has signed it. Oh, I see your point. I see.
I think we need.
So there needs to be some sort of proof. Then why do you need the gateway contract again?
Yeah, so this is for making the implementation of IO agnostic to applications. So for example, if it's okay to
What does the gateway contract do, though?
So gateway contract will technically after doing some homomorphic evaluation, this application, okay, so the role of gateway contract is check if this output ciphertext is ready for decryption or not. And in more detail, this gateway contract itself will check that the given ciphertext is like a kind of, okay, let me explain from more basis. So first, this gateway contract will manage some access control lists such that for each ciphertext, collect owner of the ciphertext is defined by the application contract address. And if some contract requests decryption for some ciphertext, it checks that this a caller of this decryption API is a rigid owner of the given ciphertext. And if this is true, it allows decryption for this ciphertext.
How does the gateway contract communicate to the conditional decryptor that it is allowed to decrypt it?
So it does not check. So basically, it's just like a trust application contract because okay, so my point is assuming that users only kind of delegate ownership of their ciphertext to some trusted application contract. This trusted application contract will some good decryption policy for each application context. So if this trusted application contract trusted by owner of the ciphertext says this ciphertext satisfies some application specific decryption policy, this gateway contract can just trust this claim as long as this caller smart contract is correct owner of the given ciphertext.
Okay.
Does it make sense?
One thing is that this gateway contract is not something that we introduce. It's already in the Zama white paper. So we are just borrowing this notion from them. It's not any novel.
I think we can keep discussion later.
Yeah, we can take it offline. Yeah.
Thank you for your question. Maybe last one question. Sorry.
About the setup ceremony, is it N of N? Does it mean that no honest, Everyone has to be honest in the setup.
So in end of an MPC, if at least one party is honest, no single party can get the hard-coded secrets.
Hello. Oh, hey, thanks for your talk. Just following up on that, so are you basically saying that for these app contracts, it's sort of like the access control list for the ciphertext, and then once those are approved, then the gateway contract can essentially evaluate it without the quote-unquote decrypting? Okay. Yeah, sorry. My other question was for the encodings that you were talking about earlier. Is that primarily for like to evaluate the actual, like, I guess FHE ciphertext? Because my understanding traditionally for something like for like the FHEVM, I think you showed earlier, usually like those zero knowledge proofs require the plain text input. I think in what I want to say you said integers, or the integer value actually for the ciphertext. So is the encoding essentially a way to do the homomorphic evaluations and verify that these were done, but you do them through the encodings instead of having to have the specific plain text be known?
I see. So the point of using this encoding is that, like, we want to allow decryption, but only for some specific circuit output, but also in a non-interactive way. So this means, for example, if we assume this obfuscator is online and the evaluator can always interact with this obfuscator, our simpler solution is that user just performs FHE evaluation and then makes a proof of the homomorphic evaluation. And that evaluator returns that circuit output, encrypted output, and the proof to the obfuscator. And the obfuscator, if obfuscator confirms this ciphertext is for specific circuit output, they just return the decrypted result. But this idea does not work since we assume this obfuscator goes offline after publishing obfuscation. So we need to make some special secret key, decryption key, such that without any interaction, this key allows decryption for some specific circuit output. But this cannot be used for any other circuit outputs. And this is actually enabled by this S times AC term. And to make such term, we need to ensure that some corresponding public key is like unique to the circuit, unique to the definition of the circuit. And also, this is independent of the input, since obfuscator cannot know evaluator's inputs beforehand in the setup.
In this example, is the trusted party here the obfuscator?
Yeah, like informally, yes. Like formally, like we have more complicated process to generate this S times AC, and actually, this term is generated during the part of the evaluation. But intuitively, yes, this trusted party is like obfuscator, and they make some enough data to allow evaluator to compute this S times AC.
Okay, yeah, so I just had one last question about the trust assumptions of the initial ceremony.
Yeah.
So, sorry if this is off base, but my understanding in something like functional encryption, for example, the master secret key, is that what is being distributed? And is that, so before that, I guess the distributed key ceremony, that the actual obfuscated circuit itself needs to be encrypted via that specific secret key, and then there's a distribution, or can that encryption can that process happen like while the keys are distributed?
Sorry, maybe I missed the last part of your question.
Sorry, basically I'm just asking, like, and again, this could be off because I'm kind of basing this off of my understanding of functional encryption. But if you're encrypting the obfuscated circuit essentially with the master secret key, this is the thing that gets distributed between the parties of the, like you said, the N of N. So does that happen like? Can you distribute the keys and then encrypt the program, or do you have to encrypt the program and then distribute the keys?
Okay, thank you for your question. So technically, like, so in the construction for decentralized obfuscation, we propose in the paper, we first make distributed secret keys for FHE using standard some kind of MPC, and but after that, each party makes obfuscation using their own secret key shares individually, instead of doing MPC for obfuscation. And this like obfuscated circuit will output partial decryption for decrypting given ciphertext instead of outputting plaintext itself. So, like if you have like n amount of the n number of the obfuscated circuit, each of which outputs decryption shares, evaluator just repeats this like evaluation of each obfuscated circuit for the same ciphertext, and they obtain the enough amount of the partial decryptions, but in a non-interactive way. And by recovering using these shares, they can recover the plaintext. And since each party needs to obfuscate circuit, which only uses their own secret key share, they don't need to perform like a MPC for obfuscating circuit. They only need this for making some secret shares of the FHE key.
Okay, cool. Thank you. Sorry. Appreciate it.
Yeah, thank you for your questions and everything.
Hello, I am Nicholas. I am with Phantom Zone, and we have been working on local mixing. You guys might have heard about local mixing throughout the talks so this week, and essentially we are working on obfuscation. Sora just talked about how I/O is very useful, and of course, there are still a lot of work that needs to be done in order to reach practicality. But this is theoretically an alternative approach to I/O. So what is local mixing? And first, it might be useful to talk about what I/O is. And this is just a quote that I liked from Huijia Lin. And the notion of indistinguishability obfuscation was first conceived by Barak in 2001. And it guarantees that the obfuscation of two circuits which are computationally indistinguishable as long as they are both equivalent circuits. So this just means that if we have C1 and C2, which on the same inputs yield the same outputs, these two obfuscated circuits would then be indistinguishable to each other. Now, local mixing actually does provide something a little stronger than this, but I will not go too much in detail, but if we have the stronger notion, then of course we will have I/O. And there are already constructions of I/O, but they have their own problems. The numerous tools that they have used in the past are evasive LWE, multilinear maps, and learning parity with noise. And of course, these have a good bit of structure. And these are also, they have a high overhead. They might be inefficient, as Sora just showed, and they are quite complex in structure. So one question that we had was, what can we achieve if we try to do I/O with only first principles, much simpler objects? This is where local mixing comes in. So let's suppose we just have a circuit. We just want to make a single perturbation. Just take a small subcircuit. We will talk about how we take these subcircuits and just change it in some way. Maybe we increase the subcircuit in the number of sides of gates, number of wires. We decrease it. Just make a small perturbation. Do it again, do it again, do it again, do it again. And the hope would then be, if we do it enough, the entire circuit, while maintaining functionality, is now obfuscated. So very simple, small perturbations that maintain functionality. So how do we actually know that this is secure? Well, our hope is that after all of these perturbations that it will look secure. And we have, I guess, two ways of actually analyzing this, but I'll talk about that later. But how effective are our randomized substitutions? Some questions that we need to answer and think about as we are making our substitutions is whether we need to expand our subcircuits, compress the subcircuits, maybe we just swap them of equal lengths. Does the overall obfuscated circuit need to grow? If it does, we think it does. How much does it need to grow? And is our injected randomness detectable? And if we do small perturbations like we just did, it will be detectable. So how do we actually hide this, and how much do we need to hide it? These are all questions that we're thinking about as we're doing local mixing. So first, just how do we select our random subcircuits? And there are kind of two natural ways to do this. Just have two circuits here. And the easy way is just to take contiguous subcircuits. Just randomly select random positions in our circuit and try to make a replacement in any way we can. The other way is to, well, not do this. We take circuits throughout the subcircuits throughout the circuit. We, of course, will make this, because if we try to replace these blocks at the bottom here without choosing them carefully, then we actually change the functionality of the circuit. So in a bit, I'll explain how we actually do this. But what type of circuits are we actually looking at? For us, we are trying to maintain simplicity. A lot of the previous tools are very complex, but if we have very simple tools, then hopefully we can get closer to practicality. And so we're going to look at reversible circuits and to Foley gates. And you might be concerned because, well, reversible circuits aren't just general purpose circuits, but we can actually represent any circuit as a reversible circuit. So this turns out not to be a huge problem. We look at the Foley gates, and in particular, we look at gates R57, which just means that on our active wire, we flip it if and only if the first control gate is true and the second control pin is false. And this actually allows us to get every gate that we would ever want. So in order to maintain simplicity, again, we look at just the single gate. And then this is just for notation. So how can we see how well our perturbations are? Well, we can make replacements, many different types of replacements, but some of our replacements will look more random than others. So how do we actually get this notation or notion of what is random and what isn't? Well, we want to have some sort of idea of a circuit isomorphism. And so we are going to define that two gates collide if an active pin shares a wire with any other pin. So here we see that the first gate, the active wire only collides with that third gate, but the second gate's active wire collides with the first gate, and then the third gate's active wire collides with the second gate. So we have some collisions here. We can't just swap these around, but if they don't collide, we can swap the gates around and we maintain functionality. So this allows us to kind of define a skeleton graph. First, we just create a node for each of our gates, and then we simply have a directed wire for each collision, and I missed one, but. So this actually allows us to look at the skeleton graph representation of our circuits when we're trying to select our subcircuits. So instead of choosing simply contiguous subcircuits, we can look at convex subcircuits. And of course, because we're looking at convexity, and in topological levels of each level in our convex subgraph, our gates are guaranteed to not be colliding. Each of these pieces we can actually swap around in order to create a version of our circuit that will have all of these sub-circuits that we've selected to be contiguous. Then we can make the replacement and ensure that we have not lost functionality in any way. So, overview of our steps in a simple way. We pick a random subcircuit, we select a random subcircuit with functionality, and of course we have now two ways of sampling our random subcircuit, and then we replace the circuit. Sounds simple enough. So what methods do we actually have? Well, first let's just talk about rainbow tables, because that third point of replacing the subcircuit is harder than it may sound. So how can we actually sample such circuits? An easy way is to do brute force. And this seems to be the one way, but I don't know another way. Maybe you guys do. And what information do we store about a circuit? Well, we have its functionality. So of course, they permute the bits that they compute on, the number of wires, and the number of gates. But if we were to store every single circuit with every single functionality, every single number of gates and wires, there are a lot. On just n wires and m gates, we can actually compute how many there are in total. And on 5 wires and 5 gates, we are already above 700 million circuits. And this actually doesn't seem that, well, this actually is quite scary because our smallest possible circuit would be on 3 wires and 1 gate. So only on 5 wires and 5 gates, we already have an explosion in the number of circuits. So we want some other notion of a circuit isomorphism. And that's where canonicalization comes from. We want to define a canonical ordering of our circuits. Our choice of canonicalization might not be the right one, but it's just a form of canonicalization. So for circuits, we can just simply keep permuting the non-colliding gates until we get an ordering, by lexicographic ordering, that is the smallest. And that will be our canonicalized circuit. Each circuit will have a permutation, and for each permutation, we can do the same thing. We can find a lexicographic ordering of the permutations up to bit shuffling. As well, we don't need to store inverses of our permutations just because if we have an inverse already stored, we can merely reverse the circuit. So this allows us to store less circuits. We only need to store our canonical circuits up to some permutation. And on 5 wires and 5 gates, we now only need to save about 3 million. Still a lot, but nowhere near as many as 5.5. Of course, this didn't actually help much as we go more wires, more gates. Our limit seems to be around 5 gates, 6 wires, 7 gates, 4, 5 wires. Or sorry, 7 wires, 4, 5 gates. So we still reach an upper limit, but we can do much better than just storing every single possible circuit. So let's get into the first thing that we tried. And this is the first method that was proposed in the paper, if you guys have seen it. In two-phase mixing, we have 2 stages. The first part, we have an inflationary phase, where we just take our circuit, find random convex subcircuits, and then try to make equivalent replacements with a larger number of gates. So we are trying to inflate our circuit in order to give it meat, so we have actual room in order to mix it. And then our second phase is the kneading phase. We just make replacements, again, using random convex subcircuits, but now we make it so that the length of our replacements are equal. So we're not trying to grow it anymore. You can think of this as you're making bread, where you first take your dough and you add more dough to make more bread, and then you knead it. You put the circuit on top of itself again and again and again, hopefully maybe thousands, millions of times, and hopefully the functionality will get randomized in the middle. So how do we actually analyze how we do? Well, one way is to look at the heat map. The heat map, we're just looking at the Hamming distance at each circuit's position along the gates. So let's say we have C1, C2 with 10 gates each. We just look at C1 at gate 1, at gate 2, at gate 3 in relation to C2 at gate 1, gate 2, and gate 3. And we can get a heat map of all of these Hamming distances. We also don't want to care about gate ordering because 2 circuits can be equivalent, but non-colliding gates are swapped around. But we know that we can just compute the canonicalization. An adversary can compute the canonicalizations. So we don't want to care about how gate ordering affects our heat maps. So this is an example of one of our early tests, where we took a 250 gate circuit and inflated up to around 20,000 and did maybe 1,000 steps of kneading. And as you can see, hopefully you can see, along the y equals x, This circuit has not changed at all. So this was very bad. This is a very scary result, because this meant that this inflationary kneading thing wasn't even doing anything. And it seems that our replacements aren't actually meaningful replacements. And in our early tests, we weren't actually using our rainbow table in order to do replacements. We were just sampling completely random circuits. But as we know that many circuits don't look that random from each other, because they may differ only by gate ordering, they may only differ by a bit shuffle. So it seems important that we actually use meaningful replacements. Here we see that we actually have, I believe this is like 1 million, maybe 2 million steps of kneading. And it actually does look more blurry. So the heat map does look more random. And so hopefully, if we did it more and more, we would get a heat map that looked completely random. And so we released the bounty. And as you may know, the bounty got this, they solved it. And essentially what happened was we released the bounty by starting with a 64-wire circuit with 1,014 gates. We inflated it up to 12,000 gates, about. Did many, many rounds of kneading, and then released the bounty with a $10,000 reward, and somebody managed to find the original functionality with even less gates. They even managed to compress our original circuit down to 987 gates. And the way they did this was by using the same thing that we were doing by inflating. We just sampled random subcircuits, made larger replacements, and no one will stop an adversary from doing the exact same thing, but instead of making replacements with larger circuits, they just make a replacement with a smaller circuit. So this is the idea of compression. And you can make a rainbow table as well, and the attacker did use a rainbow table. One thing to note is that because we're only using gate R57, 2 adjacent gates that are equal will just be the identity. So there are 2 ways to compress a circuit. One, you can just scan through the entire circuit very quickly, see if any 2 gates adjacent to each other are equal, and immediately remove them. 2, we can then look at our rainbow table, sample subcircuits, and then make replacements smaller like that. So we need to have an idea of how effective compression is. And it turns out compression on identities can be quite easy, because how can we make an identity? Well, a really easy way is to take a circuit, reverse it, concatenate it, and you have an identity. But this is very easy to compress, because as we said, adjacent gates of equal functionality will immediately get compressed. And so these can compress instantly. On completely random circuits, it is actually very hard to compress them much. Maybe they compress 1 or 2 gates, but in general, it's very hard to do so. So if we can get hard, incompressible identities, maybe this can help us. But for now, let's just look at method 2, which we call asymmetric butterfly. So let's start with just a circuit. And then in between each circuit, we insert a random identity. But it's a very stupid identity. We just take a gate, reverse it, and boom, we have an identity. And then we put them in different blocks so that each of these blocks look random. And then just focus compression on these individual blocks. Then we combine them, we combine them, we combine them, and now we have our obfuscated circuit. And then we do this for many, many rounds. And the hope here is that we can use compression. Instead of doing inflating, kneading, we do inflation, we compress. We inflate again, we compress. We repeat this again and again. And since each of these blocks are completely random, they won't compress that much, which it wasn't clear whether this would hurt us or whether this would help us. But if we can make some form of compression and stop the blocks from just staying as they are, then when we combine everything at the very end, these stupid identities wouldn't completely compress it anymore. And we would have something that is hopefully incompressible. So here's a circuit that we started with. The y-axis is flipped, but ignore that. And so we have an identity on 455 wires. We were working on sampling large identities as well, but I'm not going to go too much into detail. So we have a 450 wire, or sorry, on 5 wires, we have 455 circuit gates identity. And this was incompressible at the time. and we wanted to run obfuscation on it. The reason we chose identities is because then we could have two different identities, run obfuscation on both, and then compare how the obfuscated identities looked. And with 2 rounds of this, it looks kind of blurry, right? But we can still kind of see the structure that we had before. So we have these 4 X's, and you can still kind of see them in this heat map. And this is after 2 rounds. And if you notice, we went from 455 gates all the way up to above 300,000. So this actually impedes us a lot, because in the inflationary needing stage, we could do millions of rounds and get really nice heat maps. But now we can't do that many rounds. So that's where symmetric butterfly comes in, a small variant of the asymmetric butterfly, where we have the same steps essentially, but instead of injecting random identities in each, different random identities in between each gate, we do the same identity. And this is now, we're purposefully making each of these blocks much more structured, which would then allow us to compress it more. So it's the same idea. We want to compress these blocks so that when we combine them, they don't just immediately get killed, because super identities are easy to kill. And then later on, it will be harder to compress them in the obfuscated version. And we have some examples, and it looks questionable. We can still see the identities that we're injecting all around, and we still see a line on y equals x. So there are some questions still, but it did compress a lot more than it did prior. Another thing to note is how large are the identities that we inject. Here, the identities are about 20 gates. And red means that there's not much change. So we did essentially nothing here. And as we can see on this plot, most of the wires aren't doing anything. And most of the gates, because our identity started with 5 wires, are still dominated along those 5 wires. So we need larger wings on our identities. So what if we increase it to about 50? Okay, we can still see the X, looks a bit better. Increase it to 150, a lot better. And increase it to 300. Maybe not as good, or not as much of an improvement, but we don't really see the X anymore. But if you notice, our circuit now has blown up to 1 million gates. So when it comes to practicality, this is not ideal. We want to be able to do more rounds. And here we only did 2 rounds. And this is an example of 10 rounds on really small wings. This is also on random shooting. So here, we have canonicalized all of our circuits before computing the heat map. And I just mentioned that we don't want the heat maps to reveal anything. But there's actually another layer to this. What if we just randomly shot gates around? When we canonicalize, this wouldn't do anything. But if we look at the heat map, it doesn't get rid of the line, but it does blur things. And this idea of blurring can be very useful to us. Because what if we randomly shoot gates around, and then in order so that you can't just reverse our shooting, you can't just canonicalize, what if we combine this with our previous methods of the butterfly, so that when we insert identities that have colliding gates, you can no longer undo my random reordering of the gates. So I can fix this blurring with the butterfly method. And that's kind of what we've reached. So we have multiple ways of doing this blurring. One way is looking at method 1, where we make replacements, but instead of making just random replacements, we make much more structured replacements, where we take pairs of our gates and then make the replacement that way. And that might not seem very useful, because of course we're growing, we're going to do this butterfly thing, we're going to expand it anyway, so maybe we don't need to expand this much. But what we actually do when we replace a pair of gates, maybe 3 gates, is that you eliminate the seam in between the original 2 gates. Let's say I replace G1, G2. The seam in between G1 and G2 is now gone. It's going to be somewhere in this random replacement that we've made. Of course, the functionality is the same. But if we do this overall, we do actually see that we managed to blur the circuit. Maybe not that much, but we managed to blur it. And as you saw in the kneading that we did earlier, it does blur in the heat map. That one was incompressible, but if we combine this with the butterfly method, we do manage to become incompressible. If we compress a ton, then of course it doesn't become incompressible, but in between the rounds, as long as we don't let it kill all of our butterfly wings, eventually we become incompressible. So we have two ways of blurring. We can make it incompressible, so heat map attacks won't work because everything looks blurry. Compression attacks won't work because our butterfly method stops compression. And to me, those are the only two attacks. So there may be other methods in order to do this mixing. We chose these methods out of their simplicity. It's very quick to compute all of these things, but of course, when you try and compute these heat maps on a million gates, that's where it gets kind of tricky. Another thing we can ask is how can we sample random incompressible circuits? In the butterfly method, we insert these stupid identities, but if we can insert incompressible identities in between everything, then everything already looks random. But this question of sampling random incompressible identities is actually quite hard. We have ideas for how to do so, but they don't seem to always work out. Maybe they're still compressible a bit. They don't look that random. As you saw, that 455 gate identity had 4 of these X's. So we want, actually achieving something completely random is quite nuanced, and we don't quite know an effective way to get small random identities, but maybe we have an idea for large random identities. But of course, if we do something too large, then our butterfly method explodes like crazy. And one question we could still have is, what other attacks can an adversary attempt? I don't know one, but we plan to look at this butterfly, look at these blurring methods, and hopefully in the coming months, we're gonna release another bounty. And if someone manages to break it, well, hopefully we have a new way of studying our circuits. If someone doesn't, then we have a much better idea of how to approach local mixing. Now, local mixing won't actually achieve practical I/O, but it's another route for us to achieve I/O. And then hopefully, because everything is so simple, we can then later on reach practicality. And that's it. And then if you want to see the paper that I/O was originally, or local mixing was originally based on, there it is. Everything is open source. I didn't have a link here, but if you're curious, you can come ask me. Yes, Sora.
Thank you for your interesting talk. So my question is like, when you analyze the security of the local mixing, did you find the security of this security is essentially connected to the other layer of the cryptography, or do you think this security is completely different from the security of the other kind of cryptographic approaches?
So the security of this actually is very comparable to some security notions in physics. That's where the idea of this came from. It's not fully understood how secure this is. So our notions of security currently are mostly built on the heat maps, mostly built on the compression ideas. And one of the concerns about local mixing is indeed this lack of knowledge on how secure this would actually be in the future, which is why we do require more attempts at attacks, more adversaries. And so our hope is that as we build a repertoire of different attacks, we can get a better idea of how to establish the security of this.
I see. Yeah, technically, one thing I found is I feel your second method, I think butterfly method, seems to be somehow similar to the, I think its name is Killian randomization used for multilinear map-based I/O construction. So this also inserts some random matrix and its inverse matrix between two matrices. And if you multiply these matrices, this random path is cancelled out because random matrix and its inverse matrix is multiplied. But if you only see kind of single matrix, or if you multiply pair of a bunch of the matrices in your incorrect order, this randomization is not cancelled out, so that this makes some privacy protection. Well, like, as far as I know, I think the security provided by this randomization technique is also limited. So, like, maybe, yeah, such idea can be useful to analyze just like security of these like butterfly techniques.
Yeah, so we're still analyzing security of everything, but yeah, as you're saying, there does seem to be hope as we are unable to actually compress everything down, unable to undo this randomization. So there is hope, but of course we don't fully understand it yet.
Thank you.
Yeah, thank you.
Hello, everyone. I think they got me in to open the Overton window so that the exotic assumptions don't seem so exotic. Pause. Okay. I only have one joke, which I always tell in these situations, and no one ever laughs. But again, I'm waiting for the slide, so I'll tell it again. I went to go see my plastic surgeon recently. His name is Philip. One laugh. There we go. Yeah. So maybe I'll. One thing I wanted to say before the talk was that I was excited to come and speak to you guys today, partly because I love speaking about this stuff, but also because I think that even though on the surface what I've been thinking about is very far removed from what you guys are doing. Well, one similarity is the functionality, and I'll get to that in a second, but the other is the style of thinking, where I find myself having to reason through a lot of assumptions, security assumptions, me and many other people, through security assumptions that we need to validate. And there are different strategies and approaches, and I guess that's something that this group also has to do, especially people working with very novel assumptions. Still waiting for the slides. Okay, anyway, so I'll get you guys going on the context. So how did I end up working on this? My name is Quintus. I'm a researcher at Flashbots. And my background is actually in algorithmic game theory and protocol design. So you won't be seeing too many polynomials today. But about 18 months ago, it became quite clear that TEEs would be very, very popular and increasingly so for the foreseeable future. And I guess maybe you guys can prove me wrong. But even I think if we do get very practical I/O tomorrow, we'll still see TE usage relatively widespread, and I'll talk about that later in the talk. But I started looking into what we can do about the fact that TEEs have basically a horrible trust model. And I'll describe why it's horrible in a second, but what started off as just initial research trying to see if it's feasible to make improvements turned into a realization that we can make improvements and that there's appetite from sufficiently many parties with different specialties to make this change, to basically improve the silicon security or the world of silicon security, and that's kind of what I've been working on. So yep, this is me. And I will say that the things I talk about in this presentation will be very foreign to this group, and many of the assumptions are not validated as well as the security of AES or something like that. But at the same time, many of these are deployed today and seem to be working reasonably well. And I'll talk about that as I get through it. So the main points I'm going to get through today is that secure hardware, especially TEEs, is useful. I won't spend too much time on that. And really the point that I'm trying to make today is that secure hardware can be made more secure. And we can do this in a way that's familiar to this sort of broader cryptographic community that's used to reasoning about security in a certain way. And the implication of those two facts should be that it's worth paying attention to. So very briefly, what are TEEs? The idea is that we can build a chip in a secure manner and embed a cryptographic key in the chip. This chip will then sign the software that is deployed on it in such a way that the user can be given a certificate. This certificate then convinces the user, with some, under some trust assumptions, that they can securely interact with this program, which has been issued a private key that is sort of confined to the use of this program and is not available to anyone outside of it. Because of this, a user can interact securely with the program and is assured of some properties, even in the presence of an adversary. And the properties in the adversary are sort of vary across different devices, but broadly there are two properties that we care about. One is integrity, meaning that the program returns a correct result. We can't obviously force the chip to return a result. It can always be like disconnected from the internet or destroyed or something like that. And confidentiality. And confidentiality is underdefined. I'll explain to you guys what I think we can achieve. Some sort of manufacturers advertise complete confidentiality, that the program is completely hidden and the data that's sent to it. But that's, I think, not reasonable. It's not that hard to reverse engineer at least some of the logic that's being executed. In terms of adversaries, a high-level separation is software adversaries, which is actually where a lot of attention goes. I think these are sort of orthogonal to the things we really need to talk about. Software adversaries are a problem largely because people are trying to deal with these very large code bases and are trying to, protect against potential software supply chain bugs, or it's in the cloud setting where the cloud vendors allocating multiple tenants to the same physical machines. And so it's not actually a problem that we need to worry about, or in many cases not a problem we need to worry about if we're willing to make the trade-offs and have only the program we're trying to protect running on a chip. The more complex adversary that I'll be speaking about today is the physical adversary. And there are distinctions between physical adversaries, how long they have access to the device, and these kinds of things, and I'll get through it. But the way that the hardware research community broadly thinks about this is that the adversary is sort of parameterized by how much time they have with the device, the budget they have, the equipment they have available. And really, I think we can just think about sort of the budget they have available as a stand-in for all of those. There is also some supply chain stuff, which I'll mention in a second. So why... one of the graphics is a little bit weird, but why pay attention to TEEs at all? We have some other forms of cryptography that we can look at. One reason is performance, right? That's one of the main reasons people use TEEs right now, that they just get you attractive properties at a fraction of the overhead of what FHE or whatever else you want to use. The trust assumptions certainly are very different from what you get in MPC, for example. And so in particular, collusion and undetectable decryption attacks and these kind of things are typically mitigated with TEEs. If you speak to people who have these live MPC deployments, usually just threshold signing, they usually require the parties to run TEEs. And the third one, and the one that I think that is sort of a little bit outside of the scope of what I/O can help to address, is governance over physical objects, right? Like a camera that signs its images, so that it's not a deepfake generated image, or a surveillance camera that's attesting to you that it's not sending the feed to the NSA. This just happened this morning. I learned about it this morning. OpenAI is building a TEE privacy team. And this is the latest in a series of many announcements. Basically, the world is becoming TEE-ified. And I think this is a very important problem for us to address, even if it's ugly in the cryptographic mathematical sense. If we don't address it, we're going to end up with a world where people are relying on this very flimsy form of security. And that sort of motivates me. So briefly, what is the state of secure hardware? I'm sorry, I'm going to fly through many of these slides just because I have a lot to say and I would love to have questions at the end as well. So what is the state of secure hardware? this is a simplification, but you can kind of separate it into like different points in the trade-off curve that people have tried to occupy. I'm also reducing many dimensions here, but on the one you have sort of these cloud TEs. You've heard of Intel SGX, TDX, AMD ACV, these kind of things. These guys are just juicing out performance and doing the minimal to be able to claim, do the GDPR tick box basically. These typically don't offer any real physical security. On the other extreme, we have very small, very limited devices, like secure elements, the chips in your credit cards, your hardware wallets, these kinds of things. And these guys can't do much. These chips can't do much, but they have much stronger security than the cloud TEs. I should mention that basically all of the hardware ecosystem is completely closed. And so there are just trust assumptions implicit in that. But at least from a physical security perspective, you have this kind of separation. And one reason that I'm excited about what we're doing is, or what this like ecosystem's new demand is representing, is it's basically just asking the hardware industry, or at least I am, and I think we are implicitly with where the dollars are going, for more security. And part of the reason that part of this like space doesn't have a box in it is because there hasn't really been that economic demand for it. In fact, what we've seen over the last 10 years is that people have removed security features from, especially the cloud TEs, to juice performance because the use cases just weren't there for better security. There's also some other stuff on here, like gaming consoles or mobile phones that it's kind of hard to place them because they haven't been studied that well. Again, the whole ecosystem is very closed. But the reason I put those boxes there is just to sort of communicate that there is a very wide array of devices that have some security features in them, and they managed to achieve some level of protection. So because of these like security trade-offs, there are a bunch of like basic preventable attacks that have been published recently. These are not actually interesting research problems aside from their consideration for performance, right? So some of these things, we know how to defend against them. The question is with what overhead? And specifically these attacks, actually I'll come back to that. I won't describe it too much. It was just an absence of encryption of the way data was stored. So a story I wanted to include in here to give you an idea of what's going on is the Raspberry Pi. So Raspberry Pi at DEF CON 2024 decided to do a public bug bounty on the security features of their new chip. Which is very uncommon. People don't do this in the hardware space. Good on them. One of the submissions to the bug bounty was like very interesting. You can see sort of a screenshot from that report over here. And basically what happened was that the key storage mechanism, which had been believed to be secure for a very long time, was broken quite easily, and they demonstrated an easy methodology to take it apart. And this sent waves through the industry because it is a mechanism that had been used in many chips. And if you read the report, they say, well, we spent 90% of our time reverse engineering actually what this mechanism looks like, and then it was easy to break it. And that's a pattern you see across a lot of secure hardware research. And the other thing they said is, we were waiting for a legal window in which we can actually attack this chip. We kind of thought that this IP, we kind of thought that this mechanism was broken, but if we published it in another chip, they probably would have sued us, and we wanted to avoid that. And so there's basically just a lot of lack of opportunity to examine these things properly. Another example is Ucleak. This is on YubiKeys. It was actually a software-based attack, but it required physical access to look at the power channels. And the reason I mention that is because that was a very highly certified chip, certified to be secure. And the hardware industry, not the academics, but the industry really likes certification, which is not very good. On the supply chain side of things, there are some ways of checking that devices are not obviously backdoored. There are ways of checking it very thoroughly, which are not very widely implemented. There are many historical examples that show that the standard throughout the industry is not very good. And even for the supply chains where the manufacturer is checking, or whoever's at the end of the supply chain is checking a bit more thoroughly, that isn't exposed to the end user. And so you can't really verify if the supply chain, if there's like a backdoor basically in the chip or in the low-level software. So to summarize, people have occupied the extremes of the kind of physical security curve. I wouldn't say actually the extreme of the security curve, but because there's a third dimension of cost. But basically very small, low performance, and like pushing for security on the other extreme for performance. Closed source makes it hard to validate assumptions. The supply chain verification is an issue, and that, you know, I've spoken to a couple of people who are very enthusiastic about the idea of like unconditional security, like we just have this security assumption and no one has ever broken it and no one ever will, or like the set of security assumptions that comprise the chip. But for all intents and purposes, we assume just that there's a cost of attack and we're trying to make this very high. And then you can build protocols on top of that to amplify this kind of security. Okay, so that was all just kind of context, very gloomy, very sad. But I think there's something we can do about this, which is why I'm talking to you today. And so let's structure an approach to dealing with this. So firstly, just like what are we talking about? Well, the main functionality we want to enable here is remote attestation, meaning that the remote user can be convinced that a program is running with confidentiality and integrity on the device they expect. And so we imagine the adversary builds a device, they can choose whatever structure it should occupy. This device gets sent to some certificate authority inspection kind of mechanism, and we can choose how we implement that, and that's sent back to the adversary. The certificate authority should then like generate a certificate basically and send this to the user, and then the user will interact remotely with the chip if they want to. And this is sort of just like very abstractly how I think the flow should go, but today the certificate authority is basically just the same as the manufacturer, and so there isn't any like actual separation, but the separation of roles is important going forward. Also, if you guys have any, no, actually, let's save questions for the end. Sorry. So, okay, so in the the title of the slide is incorrect. I should just say defense strategy, physical defense strategy. So there's one thing we want to achieve, and that should basically be that the adversary should not be able to physically alter the structure of the chip beyond a certain point without irrecoverably destroying the secrets that they're trying to attack. Once we have that assumption, then we can build defenses based on the physical structure of the chip. And the physical structure implies like some level of noise. It implies some level of imprecision for fault injection because there is basically just like layers of physical matter between the adversary and the secrets they're going after. So tackling the first problem first, how do we prevent the adversary from making very profound physical changes to the structure of the device? Well, puffs, physical and clonable functions, are an interesting primitive here. I could have done the whole talk about puffs. They're very interesting. They're a relatively well-studied phenomenon. There's there's an abstract mathematical definition, and then there's like the actual practical thing that people use in silicon. And puffs are interesting because they say, let us derive a secret based on the physical structure of the chip. So in the manufacturing process, despite the best efforts of this trillion-dollar industry, every chip looks different just because of the difficulty of getting precision in physics. And if you, I'll show you guys an example in a second, if you structure your circuits correctly, you can harness this natural variation to give every chip a unique identity. And now the game is, can you design the puff so that the identity changes irreversibly if someone makes a hole in the chip, basically, and so that the secret there's sufficient entropy between the devices so that you can actually use this as a private key. And the use of puffs as private keys is like very common, or not relatively common. It's done in industry. That's not that hard of a problem. It's also used as an invasive attack countermeasure, but that is one of the like less tested assumptions in public. And of everything I talk about today, I think this is the most uncertain problem. Not that we don't have a good direction, but that basically we haven't done the physical evaluations, and that, most of the academic evaluations are done in simulation or only for the entropy side of things, not the invasive attacks. So what's an example of this? Basically imagine that your logical design says we have these wires and they're equally long. The output of the system should depend on which wire's signal terminates first. the logical description doesn't tell you which wire that should be, but the physical variations between the chips does. And it turns out that you can use this kind of an approach to realize puffs. I won't talk more about puffs because I'm running low on time. Okay, non-invasive attacks, and this is actually something that will be very interesting to this community because most of the countermeasures are based on things like leakage-resilient cryptography, or like as a subset of leakage-resilient cryptography. It started a little bit before this, but basically the seminal papers by Yuval Ashai, or this ISW basically, with the question, can you guarantee secrecy if an adversary can eavesdrop on your brain? And yeah, there's a lot to say here. It's a very mature field of research, and what's very promising about it is that there's a mature sort of pipeline going from very abstract theory, connecting this kind of research with the rest of cryptography, all the way down to practical physical chips. Before I say more about what the kind of countermeasures look like, this is the electromagnetic radiation coming off an ARM processor doing division on different values. This is okay, this is the average of several runs, but you can tell that the electromagnetic radiation gives off a lot of information. It's easy to eavesdrop that way. And so what do these countermeasures look like? Just like with the rest of cryptography, you exploit a asymmetric relationship between the attacker and the defender, where the defender pays some polynomial penalty to put an exponential penalty on the adversary. And in the case of these kind of like physical side channels, the defender is paying in terms of latency of the computation, or in the surface area, like the number of gates basically in the circuit, and the adversary pays or like is punished in terms of bits per second. And if we can make the bits per second small enough, then it requires like an infeasible amount of time to extract a secret. So the like high-level approach that's most promising here is basically like running MPC on the same chip. So it's one party, but there's multiple circuits that are executing over different shares representing the data. And it turns out that you do all these reductions to like relate the amount of noise that the adversary is experiencing versus the number of shares in your computation. I won't actually go through the history of this field. I want to point out that it's gone through several iterations where the theoretical models have been adjusted to be more realistic back and forth. And then eventually, in 2020, there was this notion of arbitrary composability. And what used to be a very arduous thing to implement now became something that you could do automatically, basically with like a compiler taking an insecured circuit to a secured one. And so in 2021, the first like automated generation of secure circuits was done. And now the tools are getting much better. Basically, the blue you can see is the automated generation of these secure circuits, and the colorful ones are the sort of bespoke, handmade ones. And this is very important because it turns out chips are very complicated, the circuits are very large, and if you have to pay a bunch of PhDs to make the thing secure, you'll be bankrupt, and probably it won't be secure because there's human error involved, and you'll only have the chip in a couple of decades. So the automated stuff is very promising. So where does this leave us? Basically a similar trajectory has gone down for fault injection. It's a couple of years behind. But through the use of electromagnetic pulses or alterations of voltage, the adversary can also inject faults in the circuits. And through using redundancy and just clever encoding schemes, in particular polynomial secret sharing or masking, you can protect against these kinds of faults relatively effectively, but the cost is still a bit high. Anyway, okay. Leaving that aside, assuming we've fixed fault injection and we've implemented masking in a sufficiently performant way, where does that leave us? The adversary shouldn't be able then to distinguish between the different data being fed to an operation, like the different values, the division operations operating over, but the adversary can distinguish different instructions from each other, and it can obviously monitor information leaving the chip. In particular, it can monitor the communication with off-chip RAM, you can encrypt the data, but you still have to tell the RAM controller which locations you're accessing. Okay, we went through that. And this leads us to this property called memory trace obliviousness, which you may know from interactive MPC. The basic idea here is if a program satisfies memory trace obliviousness if the adversary can monitor all the instructions, know the sequence of instructions, and know the sequence of memory addresses that were accessed, but cannot distinguish the secret data. And we can design the processor to make it much easier to realize this. Like, for example, if at every clock cycle you execute every instruction, this becomes much simpler. And so that would be more than just implementing masking. So I won't go into that too much. Oblivious Labs has done some really cool stuff in doing efficient implementations of ORAM, which help to realize memory trace obliviousness. It's gotten practical recently. So Oblivious Labs is like Elaine Shih, basically, and her PhD students. If you guys are from the NPC world, I guess you'd know her. You hear about Spectre, Meltdown, all these sort of like out-of-order execution, speculative execution kind of attacks. We could just not speculate on data and not have to worry about those, but that gives you a performance penalty. Fortunately, there's a bunch of research that allows you to like have the best of both worlds. I don't want to get into that, but I'm just mentioning it. I should talk about the supply chain. That's one of the things that crypto people really care about. Basically, the imaging technologies are pretty good, but they're destructive and expensive. And so the question is, how can we, when I say imaging, I mean like physically, visually, well, through microscopes, inspecting a chip and comparing it to a design. That technology is really reasonably good, but expensive and slow. So we're trying to do that in a way that's like more scalable and non-destructive. And this is some interesting work in that direction. I'm running out of time, so I won't talk about it too much. And there's actually a bunch of different techniques you can combine together to make these kind of inspections more thorough. Like, for example, you can design a chip to be more easily tested. You can monitor the power consumption properties and these kinds of things to detect if there are alterations in the logic. This is also a developing field, but I think it's maybe, it's probably also the least pressing of our concerns. I think there's just a lot of other more important problems. So if the chip which we're working on doesn't perfectly 100% guard us against Trojans, that's probably okay, because it's also really hard to, really expensive to insert at least the most advanced ones. So now this is kind of the main question that I get. Maybe it's strange that I address it at the end of the presentation then, but basically the question is, okay, so I give you a physical chip, and I give you some mechanism through which to compare the physical chip with an advertised design. We assume that works 100% with 100% guarantees. What then? We assume the user is remote, so this physical inspection process means nothing to them. Well, basically, you then have to bootstrap some protocol where you have a decentralized set of inspectors, and the logistical aspects here become the bottleneck. But imagine some hypothetical world where we could send the chip to N verifiers who could non-destructively image this chip. Then the end user only needs to trust one of those verifiers or the signature from one of those verifiers in order to sort of buy into the mapping between the physical structure and the underlying cryptography. Yeah, thank you. I'm nearly done. Open source is really important. We need to validate security assumptions. Like I said, it's currently really hard to look at commercial chips because they have NDAs and all these different kinds of things, and that makes it hard to do. I won't actually talk about this too much. The main point I want to make here is that there's levels to open sourcing silicon. So there's some IP which belongs to like the chip design team, and they can open that up. But then there are these things that like are analogous to software libraries basically, and they can't open source those IP blocks without getting permission from the vendors of those. And then there's the stuff that sort of depends on the fab on the factory that makes these things, and that's the hardest kind of thing to open source. But people are working on this, including Vitalik's new Vensa initiative, which you guys may have heard of. So closing thoughts, TEs are very important. If you guys succeed, maybe less important, but I still think important at least for the physical world. If you guys don't succeed for the collusive world, or the collusive aspect of MPC, and if the FHE people don't do a good job, then also just for performance. We need to bring cryptographic thinking and verifiability into this field. The researchers do have this kind of, when I say cryptographic thinking, I mean deriving proof of security from minimal assumptions. People have done this, especially for the non-invasive attacks, physical side channels and fault injection, but for the invasive attacks like puffs and for the supply chain, that has been less the case, and that's something I'm trying to work on. One thing that's just very hard here is that we have long cycles and high costs. So you want to try something, it takes many months, if not years, to actually bring it into a physical form. And then to validate that is expensive. And if it's broken, you have to go through the cycle again. It's not as easy as doing basically a software test to see if there's any correlations. Many assumptions need to be made. You can't do it off just a single assumption. But at the same time, despite all these challenges, there are very many low-hanging fruits. Like I said, the cloud TEs right now, which everyone's relying on, are just built purely for performance with a little bit of security, basically only against software adversaries. And so it's not that hard to get them to be much more secure. And I think not crazy hard to make them much more secure without ridiculous overhead. This is a new meme I'm trying to spread throughout the world. Sink it into your eyeballs for a second. Sovereign silicon, very exciting. And yeah, basically most of my time is now going into what is called the Trustless TE initiative at the moment. We are working to produce an open source, physically secure TE, asterisk in the next 3 years, but we're also supporting some secure hardware R&D around puffs and side channels and these kinds of things. And I have left very little time for Q&A, but yes, thank you very much for indulging these exotic assumptions. That sounds great. Are you putting your hand up for a question or? Yeah. Oh, there's the mic.
Yeah, thank you for your interesting talk. So I have 2 questions. So first point is about PUF. Mm-hmm. So as far as I understand, I think weak PUF is just a constant function which returns some secret unique to each device.
Yes.
So can we restrict that or this PUF output can be available only for some cryptographic operation without revealing?
Yes, that is how it works, right? So the puff is like a physical object. You stimulate it, out comes some value, which you can interpret as a secret key with a few extra steps. But obviously, if you then just if you make it possible to just read out that secret key with a function call, then obviously it's not secure. So basically you have to wrap that with some signing logic or encryption logic or whatever you're doing.
I understand, thank you. So my second question is about the idea of running MPC in the same hardware. Yeah, so I don't understand why it kind of makes sense from the cost performance perspective, because let's say we need X amount of cost for attacking one chip which has one threshold, one secret share, and even if we have a n chips and a circuit of chips, each of which contains different secret shares, we just need to repeat the same attack or n times, so that attack cost is just n times x, but we need to increase the area size of the hardware also n times. So what's the
so the question is, why would I run MPC on the same chip when I could run MPC between multiple chips, when doing it between multiple would have a higher attack cost?
Yeah, so what's the biggest motivation to introduce?
It's performance, right? If I say running MPC on the chip, that's basic. You can do that in a circuit in a few clock cycles and a few like nanoseconds, but like you couldn't even get a packet to another chip in a couple of nanoseconds, right? So from a performance perspective.
Sorry, I think we can discuss later. Yeah.
Okay.
Yeah, thank you.
Thanks for listening and the questions.
Thank you. We have a panel now.
So, hi guys. My name is Enrico, and I work with Sora on I/O in the Machine I/O team. And yeah, so basically now we have this panel, and all the speakers are here, and we're gonna discuss more. So I think the first question that I want to ask the panelists is more about their personal path into I/O, or actually, let's say first, because we have like Jay and Sora here are working on I/O from more like a mathematical, let's say cryptographic-based approach for the security of the obfuscation, while Quintus is more working on a hardware approach. So I think during this panel we can just say obfuscation as a way to hide, as a, let's say, this kind of abstract compiler that allows you to hide the inner working of a program and give you this obfuscated program, but we are not going to specify, or maybe when we specify, we are going to explicitly mention it, how we are going to do this obfuscation, either by mathematics or with hardware. So the first question that I want to ask the speakers and the panelists is how they got into I/O, or how they got into obfuscation, and what was the original motivation for you to join this kind of very hard challenge. So we start with Quintus, maybe.
Thank you. Yeah, I consider, I don't ever say this, but I consider myself to be working on I/O with just very exotic assumptions. Not that I exactly know the mathematical definition, but anyway. The reason I'm working on this is because I was doing mechanism design, basically, and saw the power of TEEs in the crypto space and beyond. And like I said, it became clear that they're going to be deployed everywhere and used for many things. But if we don't address them and address the shortcomings in TEEs, I think we basically build a world in which we rely on the extension of the good favor of large organizations, Intel, NVIDIA, the cloud providers, which is, I think, a marginal improvement over what we have today, but a significant shortfall of what we would like to achieve one day. Sorry?
Yeah, so basically motivation is almost same as what I talked in the first part of the talk about, like more intuitively, I think. Yeah, this is because I want to let smart contracts have some secrets that like no human can know, but like everyone can use, or in some restricted way, or in more like a stronger like a fundamentals, trust models. And yeah, my motivation, I think, I originally started Ethereum because I thought we can make some strong program. We can make programs as strong as like physical laws, like in similar to no one can modify like stop physical laws. Like we can make programs on Ethereum such that no one can alter the program, no one can stop that, no one can be ruled out, or even for deployers. And but like later I found its functionality is limited because it's completely public and it can only modify some state on Ethereum itself. But like by using cryptography, we can extend this functionality, and especially if we can make practical I/O without introducing any additional trust assumptions, like we can naturally extend this like power of smart contracts, and yeah, we can make more kind of strong and elegant smart contracts. And yeah, this is so this is the conclusion is like yeah, we can be more, smart contract can be more close to physical laws.
Thanks, Jay.
Well, so the reason that I started working on, I would say, obfuscation or obfuscation based on more exotic assumptions, is because so initially I was working on pleomorphic encryption and so on and so forth, and other cryptographic primitives. There could be multiple reasons we could figure out, but what I really want to build at the end of the day is to have like, we think of Ethereum as, like, there's the world computer. That's one way of looking at it. What I want to have is like a way to have certain parts of this world computer encrypted, hidden from anyone else, and be it hidden, be it with cryptographic guarantee. Like, I think it's very hard for us to imagine that one would be willing to use this computer if I have to trust an MPC committee for it. The only way we can do that is we have trustless cryptographic primitives, or even like trustless T in future, to be able to sort of like claim that you can use this thing as a user of blockchain systems.
I would say that I think your trustlessness is stronger than my trustlessness, because for me, you always have the supply chain issue.
Right, I see.
Yeah. Unless you inspect it yourself, but that's a lot. Yeah.
That's it.
So I think you both alluded to that, also Quintus a bit. But I think in the previous three presentation, we never touched on the actual application of this obfuscation. So what I wanted to ask you is like, yeah, this sounds very cool in theory and sounds a very challenging task that we all want to solve. But like, what you think is going to be the moment or the application that is going to drive demand for that, and therefore also drive researcher and more resources to try to solve this task? So maybe an analogy would be, we know that ZK got this big boost because of ZK rollups, that they made money flow into the market, into the business, and into research. What do you think would be the analogous case for IO? This time we start with you, Sora.
So I think in short term application can be like a trustless Bitcoin bridge, because as far as I know, this has been a kind of long-standing program, and there are various like services for bridging Bitcoin to Ethereum, but I think all of them rely on either trusted hardware or some trusted committee, different from Bitcoin miners and Ethereum validators. So like, and also from technical perspective, if we can make witness encryption practical, it's like somehow we can make a trusted Bitcoin bridge by using known techniques. So yeah, I think this can be a kind of one milestone application, both from like a demand perspective and a technical perspective. And in more longer term, the application which seems to be like important and interesting can be running the AI inference process, entire AI inference process within the obfuscated circuit. And this is especially important when people start putting their private data, not only some text data, but also like a video, like photos, sounds, they like in their like a usual daily life, and also like when one single AI model, AI agent, starts like using not only one person's private data, but also like multiple users' data, or when like a country, like a city, start using some AI services for public services, so that single AI model, or not single, but like some AI models need to like make some outputs based on like a lot of number of peoples, for private data of a lot of number of peoples. And in such cases, we need some like a kind of private world computer, and if we can like run obfuscation in your data center to make every output of the kind of AI services like ChatGPT, I think this can be a super great milestone.
And what is the trustless Bitcoin bridge, and why this is important?
So your first question is, what is the trustless? Yeah, so basically this is just a bridge between Bitcoin blockchain and Ethereum. So you can, if you deposit your Bitcoin into some like a specific Bitcoin address, you can issue a wrapped version of the Bitcoin or Ethereum. And if you ban this wrapped Bitcoin, you can withdraw Bitcoin on the Bitcoin blockchain. And we say this is trustless, especially when we don't need to rely on like any trusted hardware or any like committee like beyond the Bitcoin and Ethereum miners/validators.
Which is the case today.
Yeah, except for initial trusted setup.
Yeah. Jay, what's your take?
Well, use cases. No, I think, okay, it is nice that you guys touched upon trustless Bitcoin bridge, because if I'm not sure whether someone is familiar with the numbers, but the amount of Bitcoin that is logged on MPC-based committee bridges from Bitcoin to Ethereum is like just less than 1% total supply of BTC. So that showcases that people understand that these MPC-based systems are fragile. No one's willing to trust their money on them, unless you're a degen speculating stuff. And this sort of like, goes to, this sort of is a good bridge to my next point, which is that, we would be able to have private smart contracts or have, this encrypted private world computer using MPC committee, probably, have MPC stuff, or probably TEs as well. But the amount of value that these committees can unlock, like the amount of value that you can lock or like keep private or like, put inside these systems would not be greater than the amount of value that is required to break them. Which is obviously not, trillions of dollars. It's like, I don't know, what is for TEs, I don't know.
I think a couple thousand. I think it depends on the TE, but I think honestly, actually less. If you have physical access to one of these cloud TEs, like $50, maybe.
Yeah, but probably you can figure out that that they would not want to risk their shares on Nasdaq.
Yeah. If it's in a data center, then it's the economic argument.
Yeah, but I would say that it's not, I don't know, more than the market cap of these companies. But if we sort of like look at the trajectory of Ethereum and Bitcoin, they're going to lock, I don't know, trillions and trillions of dollars. And if you want to have privacy in those systems, you would want some cryptographic guarantees. You would want to trust into math. You cannot trust on, hardware, or I don't know how the trajectory of hardware progresses. Probably we are able to do that with hardware as well. But I don't think we can rely on MPC systems at least.
And I also, for Quintus, I also want to extend the question to your experience with application, because I know you work with Flashbot, so they use TE in production, right? So maybe the question is like also, what's the application today, and what will be the eureka moment in the future?
Right. So, coming from a game theory mechanism design background, most of the issues that people think about in mechanism design are about information. Can you get agents to reveal truthfully their information? How do you deal with this information? What information do you expose to agents? It's all about information. And so having means to technically control the flow of information is very important for this mechanism design where you can't rely on a trusted party. In concrete terms, in the blockchain space right now, basically there's all of these problems that sit between the user and the blockchain. Sometimes it's just getting a transaction on the blockchain. Threshold encryption is a solution that could work here, again, with some trust assumptions, but from an incentive perspective, people don't do it because for a variety of reasons, you want to do computation on the transactions before you put them on chain. Do you also want to do counterparty discovery? So here's a very concrete example. I am a user, I want to do a trade. Someone else has some trade routing algorithm that can help me execute my trade effectively. That trade routing algorithm is proprietary, it's how they make money. My trade is sensitive data because if they learn what my trade is going to be, they can front run me and make money off me at my expense. ideally we get these parties together. Right now we're doing it by putting the algorithm in a TEE and having the user send their data to the algorithm and basically delaying any information leaving the TEE by, let's say, a day, a parameterizable amount, and except for data flowing back to the user. So the user gets their like routed trade, for example. But just think about the internet, right? Social media apps, search. Those are probably some of the biggest areas that we haven't gone into. Data, ad auctions, more than search. And I think the reason the crypto industry hasn't even tried to go that direction is performance, and because we don't have anything for privacy, and those are all data-based applications.
Right. So I think to conclude, I want to ask you a more speculative question. I mean, these were already speculative, but this is even more speculative. So obfuscation is often deemed as this kind of end game of cryptography, this holy grail of cryptography, that basically it seems that like once we get there, there's like nothing else to work on. So it's game over and we're just gonna have holiday, I don't know. So I'm wondering, in your opinion, assuming that we get I/O, assuming that we get it in a practical way, what's gonna be the next thing, the new challenge to solve after that? And I need to ask Jay first, just for, I see you wanted to speak, Sora. If you
okay, so my answer is quantum cryptography. So like cryptography using quantum features, properties of the quantum bits. So for example,
also explain why this is different from post-quantum cryptography.
Yeah, right. So post-quantum cryptography is still using only using classical computers. But like their construction is secure even against adversaries who can use quantum computers. In contrast, quantum cryptography uses quantum bits by even by some trusted, honest parties. And this also leverages properties provided by quantums. So for example, one good example is like a one-shot signature. So if you have signing key, basically you can just reuse the signing key many times. And this is why we need blockchain to prevent double spend attack. But you can just sign two different conflicting transactions using the same secret key. But if we can use quantum-based one-shot signature, this signing key can be protected by as a quantum or superposition. And even if you have this quantum bit, you cannot reuse the same secret key, same secret quantum bit for signing two different messages. So in other words, if you can verify that you have signature by generated by this signing key in this one-shot quantum secret key, you can already convince that the same key will not be used for any other message.
Right. So the difference between classical cryptography and quantum cryptography is that basically data have this property of just decaying after being used, right? So you cannot just copy the bits infinitely, but they just as soon as you consume them, they just disappear, or you
cannot clone the private information of the quantum bits.
Jay, what's your take on this?
Right. Well, it's a very fascinating question, and to be very honest, I'm a bit short-sighted on this. I think if in case we get obfuscation, then I would say it would at least take a decade or like half a decade to build the tools so that the world can use it. And I think my focus would be that.
Okay, so that's then prompts me with another question, like how would people in 5-10 years use obfuscation, and how would they, what's going to be this obfuscation? Like how is it going to look like?
Okay, right. At the moment I just only have tools with my mind can only work with things that we know, right? Seems like and I'm going to be again a bit short-sighted and be like, I'm going to talk about the things that I know. I don't know a lot of other methods of doing obfuscation. Let's just say local mixing, for instance. I would say that if local mixing works out, and hopefully, it's a very speculative idea. I can clearly see a path of building a virtual machine out of it. So the cost on the developer side would not be much. The majority of the time would be spent on trying to figure out how can we build a VM and make and endo this particular thing a circuit with a state. I'm not sure whether the same path would be followed by the encoding method that sort of was describing about. But I see a general pattern where you take a cryptographic method that initially works with circuit, but turns out that once you can sort of like build a universal circuit using this cryptographic method, everything is solved on the developer end. Does that make sense?
Yes, absolutely. And Quintus, you have any opinion on this?
Yeah, I want to design the mechanisms, but so please can we get the tools? Then there's a lot of mechanism design stuff to do. You guys can do the rest.
Yeah.
Yeah, I think one limitation from my untrained understanding is that you guys don't get statefulness from IO. I don't know. Do you? Can you implement one-shot signatures? With
I think if we also assume Ethereum, trust in Ethereum, we can actually do one-shot signatures.
Like if you have broadcast, if you have a public broadcast that everyone can trust, like a DA,
I see.
Then you have statefulness.
So one question. Yeah, Nicola.
What I'm saying is you cannot do one-shot signatures with.
Oh yeah, that's true.
If you want to use one-shot signatures to build, say, an alternative blockchain,
Yeah.
you cannot go back and say,
Yeah.
we can have one-shot signatures.
Yes. Yeah.
Doesn't Honey Badger is a consensus protocol that's built where every node is a consensus protocol? Okay, that's completely besides the point. But yeah.
What I'm trying to say is that there is a difference, unfortunately, between what classical hardware can offer and what classical obfuscation can offer.
Right. Yeah.
Yes. So we have real one-shot signature with quantum cryptography, right?
With the lack of, to our best understanding today.
Yes.
It's unclear that what's written in the one-shot signature paper is secure or is a construction.
Oh, I see.
Yeah. If my understanding is correctly, if my understanding is correctly, the original construction of the one-shot signature was attacked later, right? Yeah. So this is why you said we don't know whether this is secure or not, right?
Anything that has new assumptions.
Okay.
Clear.
I see.
This assumption number whole.
So.
Even if they come up with a new construction, I think most of the quantum mining designs have this weird new assumptions.
Yeah.
So maybe they are safe, maybe they're not.
Yeah, I see.
So one last question just for you, Quintus. I think in the paper that we shared, read our paper. The paper we shared, we proposed this construction. We try to minimize what's inside this obfuscated program to the minimum, and we kind of outsource stuff to external, more efficient stuff, which in our case is FHE rather than obfuscation. I'm trying to understand, and actually we claim that we only need this program to be obfuscated to then have obfuscation for any program. Is it also something that you, sort of like a design pattern that you follow with TE, or it's going to be like, I don't know, millions of TE for each application?
Yeah, so this is a very practical concern that people think about, even for TEs today, called like TCB minimization, like trusted compute base. The more lines of code or more like pieces of logic you trust, the larger the chance that there's some mistaken security. Either software attack is possible, or some of these power-based attacks or something like that. And so, yeah, that's definitely something I've been thinking about. there's some interesting, like, there's this paper, there's a line of research that was started by, I think, a paper from Dan Bonnet called Slalom, which basically says, like, what if we only trust some, like, non-parallel, like, slower computer, but we still want to do LLM neural net computations with a parallel accelerator? So we do, like, all the nonlinear operations in the slow CPU, basically, and outsource all the heavy computations, the matrix moles, to the GPU. And that kind of thinking is very interesting. There's also some, there's a bunch of people looking into this. From a software perspective, it's relevant. People have, like, you know, non-cryptographic solutions for today's stuff, and for tomorrow, I think we need to come up with more secure schemes. Definitely the ideal constructions involve multiple of the acronyms, TE, MPC, you know, you pick your favorite, put in a pitch deck, and
raise money.
Sorry?
And raise money.
Yeah.
Okay, so I think the obfuscation day is over. For the last one that remain, we also have a t-shirt of Machina.io, so yeah, just come and pick up your t-shirt. Thank you, guys.
Thank you.